Welcome to our deep dive into one of the most fascinating questions in modern cosmology. Is the universe inside a black hole? Today, we'll explore this intriguing hypothesis, examining the scientific principles and theories that support it. To understand this idea, we first need to grasp what black holes are. Black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. They form from the remnants of massive stars that have ended their life cycles. The hypothesis that our universe might be inside a black hole isn't as far-fetched as it sounds. It's rooted in the principles of general relativity and quantum mechanics. These two pillars of modern physics describe how the universe behaves on both the largest and smallest scales. The notion emerged from considering the similarities between the mathematical descriptions of black holes and the observable universe. Some scientists propose that the entire cosmos could be the interior of a massive black hole existing in a larger universe. This idea challenges our traditional understanding of the universe's structure. Typically, we think of the universe as an ever-expanding entity that originated from the Big Bang. However, if we're inside a black hole, our perspective on space and time would fundamentally change. One of the most mind-bending aspects of this hypothesis is the concept of the event horizon. The event horizon of a black hole marks the boundary beyond which nothing can return. In this model, the edge of our observable universe could be analogous to an event horizon. Furthermore, inside a black hole, the laws of physics as we know them begin to break down, especially near the singularity, the point of infinite density. This aligns with certain cosmological observations that suggest our universe's extreme conditions in its earliest moments. The implications of this hypothesis are profound. It suggests that there might be a parent universe outside our black hole, which could be part of a larger multiverse. Each black hole in our universe might, in turn, contain its own universe within it. While this theory is still highly speculative, it has garnered interest because it offers a unique solution to some of the biggest mysteries in cosmology, such as the nature of dark matter and dark energy. These phenomena might be easier to understand if we consider the possibility of other universes influencing ours. As we continue to explore the depths of space and time, hypotheses like this push the boundaries of our understanding and encourage us to think beyond the conventional. Join us as we delve into the evidence, theories, and debates surrounding the idea that our universe might be inside a black hole. Black holes are among the most mysterious and powerful objects in the universe. They possess gravitational pulls so intense that even light, the fastest thing in the universe, cannot escape once it passes a certain point. The boundary around a black hole beyond which nothing can escape is known as the event horizon. It's often referred to as the point of no return. Once an object crosses this threshold, it is inevitably pulled towards the black hole's center. Inside the event horizon lies the singularity, a point where the curvature of spacetime becomes infinite. This means that gravity is incredibly strong, and the laws of physics as we understand them cease to function normally. The size of a black hole is often described by its Schwarzschild radius, which depends on the black hole's mass. The more massive the black hole, the larger its Schwarzschild radius, and therefore its event horizon. Not all black holes are created equal. Stellar black holes form when massive stars collapse under their own gravity. These are typically between a few to several tens of solar masses. Supermassive black holes, on the other hand, exist at the centers of galaxies, including our own Milky Way. These behemoths can be millions to billions of times more massive than our Sun and play crucial roles in galaxy formation and evolution. There are also intermediate mass black holes, which are less common and exist in the range between stellar and supermassive black holes. Their origins are still a subject of active research and debate among scientists. Black holes can be detected through their interactions with surrounding matter. As matter spirals into a black hole, it heats up and emits radiation, which can be observed with telescopes. This is how astronomers infer the presence of black holes. Another key feature of black holes is their ability to warp space and time. According to Einstein's theory of general relativity, massive objects like black holes cause a curvature in the space-time fabric, affecting the path of light and the flow of time itself. This warping effect leads to phenomena such as gravitational lensing, where light from a background object is bent around a black hole, creating multiple images or rings of light. This effect can be used to study black holes and their properties. Black holes also emit Hawking radiation, a theoretical prediction by physicist Stephen Hawking. This radiation results from quantum effects near the event horizon and causes black holes to lose mass and energy over time, potentially evaporating completely. Despite their name, black holes are not empty voids. They contain a tremendous amount of mass compressed into an incredibly small volume, giving them their extraordinary gravitational pull. This mass can come from stars, gas, dust, or other black holes that merge with them. When black holes merge, they create powerful gravitational waves, ripples in spacetime that can be detected by instruments like LIGO and Virgo. These waves provide valuable information about the properties of black holes and the nature of gravity. The study of black holes is not just theoretical. It's supported by a wealth of observational evidence, including the imaging of a black hole's event horizon by the Event Horizon Telescope in 2019, which provided the first direct visual evidence of a black hole. Understanding black holes is crucial for our knowledge of the universe. They challenge our understanding of physics and provide insights into the fundamental nature of matter, energy, space, and time. The formation of black holes is a dramatic process rooted in the life cycles of massive stars. When a star with sufficient mass exhausts its nuclear fuel, it undergoes a catastrophic collapse under its own gravity. During its lifetime, a star generates energy through nuclear fusion, which counteracts the force of gravity. However, once the star runs out of nuclear fuel, fusion ceases, and there is no longer any force to counteract gravity. For stars much more massive than our Sun, this collapse results in a supernova explosion. The outer layers of the star are ejected into space, while the core collapses into an incredibly dense point. If the core's mass is above a certain threshold, it continues to collapse, forming a black hole. The density and gravitational pull become so intense that nothing can escape, leading to the creation of an event horizon. This process marks the birth of a stellar black hole, which typically has a mass between a few to several tens of solar masses. These black holes can be found throughout our galaxy and others, often in binary systems or dense star clusters. Supermassive black holes have a different formation history. They are found at the centers of galaxies and have masses ranging from millions to billions of times that of the Sun. Their formation is less well understood, but it is believed to involve the merging of smaller black holes and the accretion of vast amounts of matter over time. Another possibility for the formation of supermassive black holes is the direct collapse of massive gas clouds in the early universe, bypassing the star formation stage altogether. These direct collapse black holes could have served as seeds for the growth of supermassive black holes observed today. Intermediate mass black holes, which are less common, might form through the merger of smaller black holes or the collapse of unusually massive stars. They are thought to exist in environments like globular clusters, where stellar interactions are frequent. The discovery of gravitational waves from black hole mergers has provided new insights into black hole formation. These waves, ripples in the fabric of spacetime, are produced when black holes collide and merge, offering direct evidence of such events. Another intriguing aspect of black hole formation is the role of gamma-ray bursts. These highly energetic explosions, observed in distant galaxies, are thought to be associated with the formation of black holes, possibly from the collapse of massive stars or the merger of neutron stars. Primordial black holes are a theoretical type that could have formed in the early universe, shortly after the Big Bang. These black holes would have formed from the collapse of high-density fluctuations in the early cosmic plasma, differing significantly from those formed by stellar processes. Black holes can also grow by accreting matter from their surroundings. In binary systems, a black hole can pull matter from a companion star, forming an accretion disk that heats up and emits X-rays, making the black hole detectable. The growth of black holes is not limited to stellar processes. They can merge with other black holes, gradually increasing in mass. These mergers are powerful sources of gravitational waves, which have been detected by observatories like LIGO and Virgo. The formation and growth of black holes play a crucial role in shaping the structure and evolution of galaxies. Supermassive black holes, in particular, influence their host galaxies through powerful jets and radiation, impacting star formation and galactic dynamics. Understanding black hole formation helps us piece together the life cycles of stars and the evolution of galaxies. It provides insight into the most extreme conditions in the universe, pushing the boundaries of our knowledge of physics and cosmology. Black holes come in several different types, each defined by their mass and formation process. The most commonly known are stellar black holes, which form from the remnants of massive stars that have undergone supernova explosions. Stellar black holes have masses ranging from a few to several tens of times the mass of our Sun. These black holes are often found in binary systems, where they can interact with a companion star, pulling in matter and emitting X-rays. Supermassive black holes, on the other hand, reside at the centers of galaxies, including our own Milky Way. These giants can be millions to billions of times more massive than the Sun and have a significant impact on their host galaxies. The formation of supermassive black holes is still a topic of research. They might grow by accreting gas and merging with other black holes over billions of years. Their immense gravitational pull can shape the structure and dynamics of their entire galaxy. Intermediate mass black holes are a third category, with masses between stellar and supermassive black holes. These black holes are rarer and may form through the merger of smaller black holes or the collapse of massive stars in dense star clusters. Another intriguing type is the primordial black hole. These hypothetical black holes could have formed in the early universe, shortly after the Big Bang, from the collapse of high-density fluctuations. If they exist, they could provide valuable insights into the early universe's conditions. Micro-black holes, also theoretical, are incredibly tiny black holes that could form at very high energy levels, such as those produced in particle accelerators or during the universe's initial moments. Their existence remains speculative and unproven. Kerr black holes are rotating black holes described by a specific solution to Einstein's equations. The rotation adds complexity to their structure, creating an ergosphere outside the event horizon where matter can gain energy and escape. Schwarzschild black holes are the simplest type, non-rotating and described by a solution to Einstein's equations. They have a perfectly spherical event horizon and no charge or angular momentum. Charged black holes, known as Reissner-Nordström black holes, possess an electric charge. This charge affects their gravitational field, creating a more complex structure compared to uncharged black holes. Binary black holes are systems where two black holes orbit each other. These systems can eventually merge, producing powerful gravitational waves detected by observatories like LIGO and Virgo, providing direct evidence of black hole interactions. Mini black holes are another hypothetical type, with masses much smaller than stellar black holes. These could have formed in the early universe, or could be produced in high-energy environments. Their detection would offer new insights into black hole physics. Wormholes, often associated with black holes in science fiction, are theoretical passages through spacetime that could connect distant points in the universe. While intriguing, they remain speculative and are not confirmed by current scientific evidence. Einstein-Rosen bridges are a type of theoretical wormhole described as a bridge between two black holes. These concepts arise from solutions to Einstein's equations but remain purely theoretical without observational evidence. Gravitational lensing by black holes creates phenomena where light from distant objects is bent around a black hole, forming multiple images or rings. This effect helps astronomers study black holes and the distribution of matter in the universe. The variety of black holes and their unique properties illustrate the diversity and complexity of these cosmic phenomena. Each type provides different clues about the nature of gravity, the evolution of stars, and the structure of the universe. The event horizon of a black hole is a critical boundary beyond which nothing can escape, not even light. It marks the point of no return, where the gravitational pull becomes so strong that escape is impossible. As you approach the event horizon, the effects of gravity become increasingly extreme. Time appears to slow down for an outside observer, a phenomenon predicted by Einstein's theory of general relativity. Once an object crosses the event horizon, it is inexorably drawn towards the singularity at the black hole's core. The singularity is a point where gravitational forces compress matter to infinite density and zero volume, causing space-time to curve infinitely. The event horizon itself is not a physical surface, but rather a mathematical boundary. For an observer falling into a black hole, there would be no noticeable change as they cross the event horizon, but their fate would be sealed. Inside the event horizon, all paths lead to the singularity. The immense gravitational forces would stretch and compress any object in a process known as spaghettification, tearing it apart as it approaches the core. The singularity represents a breakdown of our current understanding of physics. The laws of general relativity predict its existence, but they also suggest that densities and curvatures become infinite, which is physically problematic. Physicists believe that a theory of quantum gravity, which unites general relativity and quantum mechanics, is needed to fully describe the singularity. Until such a theory is developed, the singularity remains one of the most mysterious aspects of black holes. The size of the event horizon, known as the Schwarzschild radius, depends on the mass of the black hole. For a stellar black hole, this radius is typically a few kilometers, while for a supermassive black hole, it can be as large as the solar system. The shape of the event horizon can also vary. For non-rotating black holes, it is a perfect sphere, while for rotating black holes, it becomes oblate due to the centrifugal forces caused by their spin. The ergosphere is an additional region outside the event horizon of a rotating black hole. In this area, spacetime is dragged around with the black hole, making it possible for energy to be extracted from the black hole through processes like the Penrose process. Hawking radiation is a theoretical prediction that black holes emit radiation due to quantum effects near the event horizon. This radiation causes black holes to lose mass over time, potentially leading to their eventual evaporation. The discovery of Hawking radiation was groundbreaking because it suggested that black holes are not entirely black, but can emit radiation and lose mass. This phenomenon links quantum mechanics with the behavior of black holes. The study of event horizons has profound implications for our understanding of information and entropy. The holographic principle proposes that all information within a black hole can be encoded on its event horizon, leading to new insights into the nature of reality. The information paradox arises from the question of whether information that falls into a black hole is lost forever. This paradox challenges the principles of quantum mechanics, which state that information cannot be destroyed. Black holes, with their event horizons and singularities, continue to be at the forefront of theoretical physics. They push the boundaries of our understanding and drive the search for a unified theory of the fundamental forces of nature. Observational evidence of black holes has significantly advanced our understanding of these mysterious objects. One of the most compelling pieces of evidence comes from the detection of X-rays emitted by the accretion disks around black holes. Accretion disks form as matter spirals into a black hole, heating up to extremely high temperatures and emitting X-rays. These X-rays can be detected by space telescopes, providing indirect evidence of black holes. Gravitational waves offer another crucial line of evidence. These ripples in spacetime are produced by the merger of black holes. Observatories like LIGO and Virgo have detected these waves, confirming the existence of black hole mergers. The first direct visual evidence of a black hole came in 2019, when the Event Horizon Telescope captured an image of the shadow of the supermassive black hole in the galaxy M87. This groundbreaking image showed the event horizon's silhouette against the glowing accretion disk. Observations of stellar orbits around the center of our galaxy have provided strong evidence for a supermassive black hole. Stars near the galactic center exhibit rapid and tightly bound orbits, indicating the presence of an extremely massive and compact object. Sagittarius A, the supermassive black hole at the center of the Milky Way, has been studied extensively through radio, infrared, and X-ray observations. The motion of nearby stars and gas clouds supports the conclusion that a black hole resides there. The phenomenon of gravitational lensing, where light from a distant object is bent around a massive body like a black hole, also provides evidence. This effect creates multiple images or rings of light, revealing the presence of black holes. Quasars, which are extremely luminous and energetic objects, are believed to be powered by supermassive black holes at the centers of distant galaxies. The intense radiation emitted by quasars comes from the accretion of matter onto these black holes. The variability of X-ray emissions from accretion disks around black holes offers further evidence. These emissions can fluctuate rapidly, indicating the presence of a small dense object with a strong gravitational pull. Microlensing events, where the light from a background star is temporarily magnified by a passing massive object like a black hole, provide additional indirect evidence. These events help detect black holes that do not emit significant radiation. The observation of relativistic jets, which are streams of particles ejected at near-light speeds from the regions around black holes, also supports their existence. These jets are often observed in active galactic nuclei and X-ray binaries. Gamma-ray bursts, some of the most energetic explosions in the universe, are thought to be associated with the formation of black holes. These bursts provide clues about the processes leading to black hole formation and growth. The study of globular clusters, which are dense groups of old stars, has revealed the presence of intermediate mass black holes. The motions of stars within these clusters suggest the influence of a massive central object. Further evidence comes from the analysis of high-energy cosmic rays, which may be produced by processes near black holes. These cosmic rays provide insights into the extreme conditions and high-energy environments around black holes. Finally, the continuous advancements in observational technology, from more sensitive telescopes to sophisticated detectors for gravitational waves, promise to uncover even more evidence. These observations will deepen our understanding of black holes and their role in the universe. To understand the universe's structure, we must first define what we mean by the universe. The universe encompasses all of space, time, matter, and energy. It includes everything that exists, from the smallest particles to the largest galaxies. The observable universe refers to the part we can see or detect from Earth, limited by the speed of light and the age of the universe. Beyond this lies the entire universe, which may be infinitely larger than what we can observe. The large-scale structure of the universe is defined by a web of galaxies and galaxy clusters. These structures are interconnected by vast cosmic filaments, separated by enormous voids, regions with very few galaxies. Galaxies are the fundamental building blocks of the universe's structure. Each galaxy contains billions of stars, planets, and other celestial objects, all bound together by gravity. They come in various shapes and sizes, including spiral, elliptical, and irregular galaxies. At an even larger scale, galaxies group together to form clusters and superclusters. These massive structures can contain thousands of galaxies, bound by their mutual gravitational attraction. Our Milky Way is part of the local group, which is in turn part of the Virgo supercluster. Within galaxies, stars form the primary luminous components. Stars are born in nebulae, vast clouds of gas and dust, and evolve through various stages depending on their mass. They can end their lives as white dwarfs, neutron stars, or black holes. Planets, moons, asteroids, and comets orbit stars, forming planetary systems. Our solar system, with the Sun at its center, is just one example of countless planetary systems throughout the galaxy. The interstellar medium fills the space between stars within a galaxy. This medium consists of gas, dust, and cosmic rays, and plays a crucial role in star formation and the evolution of galaxies. Dark matter is a mysterious and invisible substance that makes up about 27% of the universe's total mass and energy. It does not emit, absorb, or reflect light, making it undetectable by conventional means, but its gravitational effects are essential for the formation and stability of galaxies. Dark energy is an even more enigmatic component, accounting for roughly 68% of the universe. It is believed to be responsible for the accelerated expansion of the universe, pushing galaxies apart at an increasing rate. The Big Bang Theory is the leading explanation for the universe's origin. According to this theory, the universe began as an extremely hot and dense point about 13.8 billion years ago and has been expanding ever since. Cosmic inflation, a rapid expansion that occurred fractions of a second after the Big Bang, helped shape the large-scale structure of the universe. This period of inflation smoothed out any irregularities, leading to the homogeneous and isotropic universe we observe today. The cosmic microwave background radiation, a faint glow left over from the early universe, provides a snapshot of the universe when it was just 380,000 years old. This radiation is a crucial piece of evidence for the Big Bang Theory and helps us understand the universe's early conditions. The Hubble law describes the relationship between the distance of galaxies and their recessional velocity, indicating that the universe is expanding. This discovery has profound implications for our understanding of the universe's past, present, and future. The universe's structure, from the smallest particles to the largest cosmic filaments, is a complex and interconnected web. By studying this structure, we gain insights into the fundamental nature of reality and the forces that shape our cosmic environment. The observable universe is the portion of the entire universe that we can see or detect from Earth. This is limited by the speed of light and the finite age of the universe. Light from the farthest regions has only had about 13.8 billion years to reach us. Beyond the observable universe lies the entire universe, which may be vastly larger and could extend infinitely. We cannot observe or measure this part directly due to the limitations imposed by the speed of light. The cosmic horizon is the boundary of the observable universe. It represents the maximum distance from which light or other signals could have traveled to us since the beginning of the universe. This horizon constantly expands as the universe ages. Galaxies at the edge of the observable universe appear as they were billions of years ago. The finite speed of light means we see these distant galaxies in their ancient past, not as they are today. This allows astronomers to look back in time and study the early universe. The observable universe contains an estimated 2 trillion galaxies, each with billions of stars. Despite this vast number, it is only a tiny fraction of the entire universe. The unobservable regions could contain even more galaxies and other structures. Dark matter and dark energy, which dominate the mass and energy of the observable universe, likely extend beyond our observable limits. Their influence on the universe's expansion and structure suggests their presence in the unobservable regions as well. Cosmological models based on general relativity and observations indicate that the universe is homogeneous and isotropic on large scales. This means that the properties of the universe are similar everywhere, even beyond the observable limits. The concept of cosmic inflation, a rapid expansion in the early universe, suggests that regions far beyond our observable horizon are part of the same universe. Inflation stretched space so much that distant regions became causally disconnected from us. The entire universe could contain regions with different physical laws or constants, depending on the theories of the multiverse. Some models propose that different regions might have different properties, leading to a diverse and varied cosmic landscape. Observations of the cosmic microwave background radiation provide insights into the conditions of the early observable universe. This radiation, however, does not reveal details about the regions beyond our observational reach. Gravitational waves offer a potential means of probing the unobservable universe. These ripples in spacetime could carry information from regions beyond our current observational capabilities, giving us indirect clues about the entire universe. The large-scale structure of the universe, with its cosmic web of galaxies and clusters, likely extends far beyond the observable limits. This interconnected structure hints at a much larger and more complex universe than what we can currently see. Studying the observable universe helps us infer properties about the entire universe. By understanding the distribution of galaxies, the behavior of dark energy, and the effects of dark matter, we can make educated guesses about the unobservable regions. Philosophical questions arise from the distinction between the observable and entire universe. What lies beyond our cosmic horizon? Are there other forms of life or civilizations in the unobservable regions? These questions drive much of our curiosity and exploration. Technological advancements in telescopes and detectors continue to push the boundaries of our observable universe. As we develop new methods to detect distant objects and phenomena, our understanding of the entire universe will expand, revealing more of the cosmos's hidden secrets. The universe operates on a cosmic scale that is difficult for the human mind to comprehend. From the smallest particles to the largest structures, the range of sizes and distances is truly staggering. At the smallest scale, we have subatomic particles such as quarks and electrons, which are the building blocks of atoms. These particles are measured in femtometers, which are quadrillionths of a meter. Atoms combine to form molecules, which in turn make up the matter we interact with every day. These molecules can range from a few angstroms to several nanometers in size, still incredibly tiny compared to human scales. Moving up, we have the scale of planets and stars. Our Earth is about 12,142 kilometers in diameter, while the Sun is roughly 1.39 million kilometers across. Stars vary greatly in size, with some being hundreds of times larger than our Sun. Solar systems, like our own, span billions of kilometers. The distance from the Sun to Pluto, for example, is about 5.9 billion kilometers, highlighting the vast emptiness of space even within a single solar system. Beyond solar systems, we have galaxies, which are collections of billions or even trillions of stars. Our Milky Way galaxy is about 100,000 light-years in diameter. A light-year is the distance light travels in 1 year, approximately 9.46 trillion kilometers. Galaxies themselves are grouped into clusters and superclusters. The local group, which includes the Milky Way, is about 10 million light-years across. These clusters are part of even larger structures called cosmic filaments, which span hundreds of millions of light-years. On these enormous scales, space is structured like a cosmic web, with galaxies and clusters connected by vast filaments of dark matter and separated by enormous voids. This structure reveals the large-scale distribution of matter in the universe. Time also plays a crucial role in understanding the universe. The universe is approximately 13.8 billion years old, and studying light from distant objects allows us to look back in time and observe the universe's history and evolution. Dimensions in the universe extend beyond the 3 spatial dimensions we experience daily. Theories like string theory propose additional spatial dimensions that are compactified and not directly observable. These extra dimensions could help explain fundamental forces and particles. Einstein's theory of general relativity describes space and time as a 4-dimensional fabric called spacetime. Massive objects like stars and black holes warp this fabric, creating the gravitational effects we observe. On the cosmic scale, gravity governs the motion of galaxies, stars, and planets. However, on the smallest scales, quantum mechanics dominates, describing the behavior of particles and the forces between them. The interplay between general relativity and quantum mechanics is a major area of research in theoretical physics. Understanding how these 2 frameworks fit together could unlock new insights into the universe's fundamental nature. The cosmic microwave background radiation provides a snapshot of the universe when it was just 380,000 years old. This radiation, now observed as a faint glow in all directions, offers clues about the universe's size, shape, and composition at that early time. The cosmic scale and dimensions of the universe reveal a vast, interconnected cosmos. From the tiniest particles to the largest structures, the universe's complexity and grandeur challenge our understanding and inspire continual exploration. Galaxies are massive systems composed of stars, stellar remnants, gas, dust, and dark matter, all bound together by gravity. They come in various shapes and sizes, from spiral and elliptical to irregular forms. The Milky Way is our home galaxy, a barred spiral galaxy with a diameter of about 100,000 light-years. It contains billions of stars, including our Sun, and vast amounts of interstellar gas and dust. Stars are the fundamental building blocks of galaxies. They form from the gravitational collapse of gas clouds and produce light and heat through nuclear fusion in their cores. Stars vary widely in size, temperature, and luminosity. Our Sun is a medium-sized star known as a G-type main sequence star. It has been shining for about 4.6 billion years and provides the necessary energy for life on Earth. Stars like the Sun spend most of their lives in the main sequence stage, fusing hydrogen into helium. Massive stars, much larger than the Sun, live shorter lives and end in dramatic supernova explosions. These explosions spread heavy elements into space, enriching the interstellar medium and contributing to the formation of new stars and planets. Planets are celestial bodies that orbit stars. They come in a variety of types, including rocky terrestrial planets like Earth and Mars, and gas giants like Jupiter and Saturn. Some planets, known as exoplanets, orbit stars outside our solar system. The discovery of thousands of exoplanets has expanded our understanding of planetary systems. These planets vary in size, composition, and orbital characteristics, suggesting a wide diversity of planetary environments. In addition to stars and planets, galaxies contain various other components. These include star clusters, which are groups of stars that form together from the same molecular cloud, and nebulae, which are vast clouds of gas and dust where new stars are born. Dark matter, an invisible substance that does not emit or absorb light, makes up a significant portion of a galaxy's mass. Its presence is inferred from its gravitational effects on visible matter, such as the rotation of galaxies and the motion of galaxy clusters. The central regions of many galaxies contain supermassive black holes, which can be millions to billions of times the mass of the Sun. These black holes can influence the dynamics of their host galaxies and power-active galactic nuclei and quasars. Galaxies can interact and merge with one another, leading to dramatic changes in their structure and triggering bursts of star formation. These interactions are an important part of the evolutionary history of galaxies. The Andromeda Galaxy, the closest spiral galaxy to the Milky Way, is on a collision course with our galaxy. In about 4 billion years, the two galaxies will merge, forming a new galaxy and significantly altering their structures. Dwarf galaxies, which are much smaller than spiral and elliptical galaxies, are also common in the universe. They often orbit larger galaxies and can be drawn into them, contributing stars and gas to their larger neighbors. Galaxy clusters are collections of hundreds to thousands of galaxies bound together by gravity. These clusters are the largest gravitationally bound structures in the universe and are often found at the intersections of cosmic filaments. The study of galaxies, stars, and planets helps us understand the structure and evolution of the universe. By examining these components, astronomers can trace the history of the cosmos from the Big Bang to the present day. The Big Bang theory is the leading explanation for the origin of the universe. It proposes that the universe began as an extremely hot and dense point about 13.8 billion years ago and has been expanding ever since. According to this theory, the universe started from a singularity, a point of infinite density and temperature. From this singularity, space and time as we know them began to expand. In the first few fractions of a second after the Big Bang, the universe underwent a rapid period of inflation, expanding exponentially. This inflation smoothed out any irregularities and set the stage for the formation of matter and structure. As the universe expanded and cooled, particles such as quarks and electrons began to form. These particles eventually combined to create protons and neutrons, leading to the formation of atomic nuclei. About 3 minutes after the Big Bang, the temperature of the universe dropped enough for nuclear fusion to occur. This process produced the first light elements, primarily hydrogen and helium, along with trace amounts of lithium and beryllium. For the next 380,000 years, the universe remained a hot, dense plasma of charged particles and photons. During this period, known as the photon epoch, light could not travel freely through space. As the universe continued to cool, electrons combined with protons and nuclei to form neutral atoms. This recombination allowed photons to travel freely, resulting in the release of the cosmic microwave background radiation. The cosmic microwave background radiation is a faint glow that fills the universe and provides a snapshot of the universe when it was just 380,000 years old. It offers crucial evidence for the Big Bang theory and helps us understand the early conditions of the universe. Following recombination, the universe entered the Dark Ages, a period before the formation of the first stars and galaxies. During this time, matter began to clump together under the influence of gravity, forming the seeds of future cosmic structures. The first stars, known as population 3 stars, formed a few 100 million years after the Big Bang. These stars were massive and short-lived, producing heavy elements and influencing the formation of subsequent generations of stars and galaxies. Galaxies began to form from these early star clusters, growing through mergers and the accretion of gas. The formation and evolution of galaxies are key processes in shaping the universe we observe today. The Big Bang theory is supported by multiple lines of evidence, including the expansion of the universe, the abundance of light elements, and the cosmic microwave background radiation. Observations of distant galaxies and the large-scale structure of the universe also align with predictions from the Big Bang model. The theory has evolved over time, incorporating new discoveries and refinements. Concepts like dark matter and dark energy have been introduced to explain observations that the Big Bang theory alone cannot fully account for. Dark energy, in particular, is thought to drive the accelerated expansion of the universe, a discovery made in the late 20th century. This expansion suggests that the universe will continue to grow larger and colder over time. The Big Bang theory not only explains the origin and evolution of the universe, but also raises profound questions about the nature of reality, the origin of matter and energy, and the ultimate fate of the cosmos. It remains a central framework for understanding the universe and continues to inspire research and exploration in cosmology. The hypothesis that our universe might exist inside a black hole originates from attempts to reconcile general relativity and quantum mechanics. These two fundamental theories describe the large-scale structure of the universe and the behavior of particles on the smallest scales. In the early 20th century, Einstein's theory of general relativity revolutionized our understanding of gravity, describing it as the curvature of spacetime caused by mass and energy. This theory successfully explained many cosmic phenomena, but struggled to account for quantum effects. Quantum mechanics, developed around the same time, explains the behavior of particles at atomic and subatomic levels. It introduces the concept of probabilities and uncertainties, which clash with the deterministic nature of general relativity. Physicists have long sought a unified theory that combines general relativity and quantum mechanics. This quest has led to the exploration of various hypotheses, including the idea that our universe might be a black hole in a higher dimensional space. In the 1960s and 70s, theoretical physicists like Roger Penrose and Stephen Hawking made significant contributions to our understanding of black holes. They developed mathematical models showing how black holes could form and behave in a universe governed by general relativity. Penrose and Hawking's work on singularities, points of infinite density within black holes, raised questions about the nature of space-time and the potential for similar conditions at the beginning of our universe. The idea gained further traction with the development of string theory and its extension, M-theory. These theories propose that our universe has more than the familiar three spatial dimensions, suggesting that black holes could connect to higher dimensional spaces. According to these theories, the singularity within a black hole in our universe might connect to a higher dimensional parent universe. This connection could resemble a wormhole, a theoretical passage between different regions of space-time. The hypothesis suggests that the Big Bang, which marks the beginning of our universe, could be analogous to the formation of a black hole in a higher dimensional space. This perspective offers a potential link between the origin of our universe and the properties of black holes. Additionally, the holographic principle developed in the 1990s by physicists Gerard 't Hooft and Leonard Susskind provides a theoretical framework supporting this hypothesis. It proposes that all the information within a volume of space can be described by the information on its boundary, similar to how information about a black hole is encoded on its event horizon. This principle implies that our three-dimensional universe could be a projection of information stored on a two-dimensional surface, possibly the event horizon of a higher dimensional black hole. Cosmologists have explored these ideas through mathematical models and simulations. These studies suggest that the observable properties of our universe, such as its expansion and the distribution of matter, could be consistent with being inside a black hole. The hypothesis also addresses some puzzles in cosmology, like the nature of dark energy and the accelerating expansion of the universe. If our universe is inside a black hole, the expansion we observe could be driven by processes in the higher dimensional space. While this hypothesis remains speculative, it has inspired new lines of research and led to intriguing questions about the nature of our universe. It challenges our conventional understanding and encourages scientists to explore the connections between black holes, space-time, and the origin of the cosmos. The idea that our universe might be inside a black hole illustrates the creativity and boldness of theoretical physics. It pushes the boundaries of our knowledge and opens new avenues for exploring the fundamental nature of reality. As research continues, this hypothesis may provide deeper insights into the mysteries of the universe and the underlying principles that govern its existence. Roger Penrose is one of the key proponents of the idea that connects black holes and the universe's origins. His work on singularities and space-time laid the groundwork for understanding how extreme gravitational conditions can affect the structure of the universe. Stephen Hawking expanded on Penrose's ideas and made significant contributions to our understanding of black holes. His theory of Hawking radiation showed that black holes can emit particles, providing a bridge between quantum mechanics and general relativity. Leonard Susskind, a pioneer of string theory, introduced the holographic principle. This principle suggests that all the information within a volume of space can be described by the information on its boundary, supporting the idea that our universe could be a projection from a higher dimensional space. Gerard 't Hooft, another leading physicist, independently developed the holographic principle. His work has been crucial in understanding how information and entropy behave in black holes and cosmological models. Juan Maldacena proposed the ADSE-CFT correspondence, a concept in string theory that relates a type of spacetime called anti-de Sitter space to a conformal field theory. This idea supports the notion that our universe might be a holographic projection from a higher dimensional reality. Nima Akani Hamed, a prominent theoretical physicist, has explored the implications of extra dimensions and their connection to black holes and cosmology. His work suggests that our universe might have more dimensions than we can observe directly. Lisa Randall, known for her work on extra dimensions, has proposed models where gravity can spread into additional dimensions. These ideas could explain how black holes in higher dimensions influence our observable universe. Joseph Polchinski, a string theorist, made significant contributions to the understanding of black holes and their quantum properties. His work on the black hole information paradox has influenced theories about the nature of black holes and their connection to the universe. Paul Davies has written extensively on the idea that our universe might be a black hole. He explores the philosophical and scientific implications of this hypothesis, considering how it fits into the broader framework of cosmology. Max Tegmark has discussed the possibility of multiple universes and higher dimensions. His work on the mathematical structure of the universe suggests that our cosmos could be part of a much larger multiverse. André Linde, a proponent of the inflationary universe model, has considered how black holes and cosmic inflation might be connected. His theories provide a possible mechanism for how our universe could have emerged from a black hole in a higher dimensional space. Savas Dimopoulos has explored theories involving large extra dimensions and their potential impact on particle physics and cosmology. His ideas support the concept that our universe might have hidden dimensions that influence its fundamental properties. Raphael Bousso, a theoretical physicist, has worked on the holographic principle and its applications to cosmology. His research helps bridge the gap between black hole physics and the large-scale structure of the universe. Brian Greene, a string theorist and popular science communicator, has brought attention to the idea that our universe could be a holographic projection. His work explains complex concepts in an accessible way, helping to popularize these theories. Tom Banks has contributed to the understanding of quantum gravity and black holes. His research focuses on the theoretical underpinnings of how black holes might connect to the broader universe, exploring the deep implications of these ideas. The scientific basis for the idea that our universe might be inside a black hole is rooted in the principles of general relativity and quantum mechanics. These two pillars of modern physics describe the behavior of the universe on both the largest and smallest scales. General relativity, proposed by Einstein, describes gravity as the curvature of spacetime caused by mass and energy. This theory predicts the formation of black holes, regions where gravity is so strong that nothing, not even light, can escape. Black holes are characterized by an event horizon, a boundary beyond which nothing can return. The concept of an event horizon is crucial to understanding how a black hole might contain a universe within it. Quantum mechanics, on the other hand, describes the behavior of particles at the atomic and subatomic levels. It introduces the idea of probabilities and uncertainties, which clash with the deterministic nature of general relativity. The quest to unify general relativity and quantum mechanics has led physicists to explore theories involving higher dimensions and alternative structures of space-time. One such theory is string theory, which suggests that the fundamental components of the universe are one-dimensional strings. String theory and its extension, M-theory, propose that our universe might have more than the familiar three spatial dimensions. These additional dimensions could provide a framework for understanding how a black hole in higher dimensional space might contain our universe. The holographic principle, developed in the 1990s, provides further support for this idea. It suggests that all the information within a volume of space can be described by the information on its boundary, much like a hologram. This principle implies that our three-dimensional universe could be a projection of information stored on a two-dimensional surface, potentially the event horizon of a higher dimensional black hole. This idea bridges the gap between the behavior of black holes and the structure of the universe. The ADS-CFT correspondence, a concept from string theory, relates a type of spacetime called anti-de Sitter space to a conformal field theory. This correspondence supports the notion that our universe might be a holographic projection from a higher dimensional reality. Mathematical models and simulations have explored how the properties of our universe, such as its expansion and the distribution of matter, could be consistent with being inside a black hole. These models help scientists test the feasibility of this hypothesis. Cosmological observations, such as the cosmic microwave background radiation and the distribution of galaxies, provide data that can be compared to predictions from the hypothesis. These observations help refine the models and test their accuracy. The nature of dark energy and the accelerating expansion of the universe suggest that there are forces at play that we do not fully understand. If our universe is inside a black hole, these phenomena could be influenced by processes in the higher dimensional space. Gravitational waves, ripples in spacetime produced by massive objects like merging black holes, offer another avenue for testing the hypothesis. These waves carry information about the structure of spacetime and can provide insights into the nature of our universe. The information paradox, which questions whether information that falls into a black hole is lost forever, also ties into this hypothesis. Resolving this paradox could provide clues about the relationship between black holes and the broader universe. Research continues to explore these ideas, pushing the boundaries of our understanding and challenging conventional notions of space, time, and reality. As new data and theoretical developments emerge, the hypothesis that our universe might be inside a black hole remains an intriguing possibility that inspires ongoing investigation and debate. Initial reactions from the scientific community to the idea that our universe might be inside a black hole were mixed, with both skepticism and intrigue. Many scientists were fascinated by the boldness of the hypothesis and its potential to unify various aspects of theoretical physics. Some physicists appreciated the hypothesis for its ability to address complex questions in cosmology, such as the nature of singularities and the origin of the universe. The idea offered a novel perspective that could potentially bridge gaps between general relativity and quantum mechanics. However, other scientists were cautious, pointing out the speculative nature of the hypothesis. They emphasized the need for empirical evidence and testable predictions to support such an extraordinary claim. Without observational data, the hypothesis remained largely theoretical. The hypothesis also sparked discussions about the nature of scientific theories and the role of imagination in theoretical physics. Some argued that exploring unconventional ideas, even if speculative, is essential for advancing our understanding of the universe. As the hypothesis gained attention, researchers began developing mathematical models and simulations to explore its implications. These efforts aim to provide a more concrete framework for the idea and identify potential observational signatures. The holographic principle and the ADS-CFT correspondence received particular interest, as they provided a theoretical foundation for the hypothesis. These concepts suggested that the universe could be described in ways that align with the idea of being inside a higher dimensional black hole. Critics of the hypothesis pointed out the challenges of testing it empirically. Observing direct evidence of higher dimensions or confirming the universe's holographic nature posed significant technical and theoretical obstacles. Despite these challenges, the hypothesis inspired a wave of research into black holes, quantum gravity, and cosmology. Scientists sought to explore the potential connections between these fields and understand how they might inform our understanding of the universe's structure. The hypothesis also led to new questions about the nature of spacetime, the limits of observability, and the potential existence of a multiverse. These questions pushed the boundaries of cosmological inquiry and opened new avenues for exploration. Over time, the initial skepticism began to shift as more sophisticated models and simulations were developed. Researchers found that the hypothesis could potentially explain certain cosmic phenomena and align with known physical laws. Collaborations between theoretical physicists and observational astronomers aim to identify possible evidence supporting the hypothesis. These efforts included studying cosmic microwave background radiation, gravitational waves, and the large-scale structure of the universe. As the scientific community engaged with the hypothesis, it became a focal point for debates about the nature of reality and the limits of human knowledge. The idea challenged conventional thinking and encouraged scientists to reconsider fundamental assumptions. The hypothesis also had philosophical implications, prompting discussions about the nature of existence and our place in the cosmos. If the universe is inside a black hole, what does that mean for our understanding of reality and our role within it? Public interest in the hypothesis grew as it gained media coverage and was featured in popular science discussions. This broader engagement helped raise awareness of the complexities and wonders of theoretical physics and cosmology. While the hypothesis remains unproven, its impact on the scientific community is undeniable. It has inspired new lines of inquiry, fostered interdisciplinary collaboration, and highlighted the importance of exploring bold ideas in the quest to understand the universe. The current status of the hypothesis that our universe might be inside a black hole is a mixture of active research, ongoing debate, and cautious optimism. Researchers continue to explore its implications through both theoretical models and observational studies. Advances in technology, such as more powerful telescopes and detectors, have allowed scientists to gather data that could potentially support or refute the hypothesis. These instruments are helping to probe the universe's most extreme environments. Theoretical physicists are refining their models to better understand how a universe inside a black hole might behave. These efforts involve complex simulations that aim to replicate the conditions and behaviors predicted by the hypothesis. One area of focus is the study of gravitational waves. These ripples in space-time, produced by cataclysmic events like black hole mergers, offer a unique way to test predictions about the structure of space-time and the nature of black holes. Cosmologists are also examining the cosmic microwave background radiation for clues. This ancient light, which provides a snapshot of the early universe, might contain subtle signatures that align with the hypothesis. In the realm of quantum gravity, researchers are investigating how principles like the holographic principle could manifest in observable phenomena. These studies aim to find connections between black holes, space-time, and the information encoded in the universe. Interdisciplinary collaboration has become increasingly important. Physicists, astronomers, and mathematicians are working together to develop a cohesive framework that can be tested through experiments and observations. Despite significant progress, many challenges remain. The hypothesis requires new ways of thinking about space, time, and dimensions, which can be difficult to reconcile with established scientific paradigms. Critics of the hypothesis continue to emphasize the need for empirical evidence. They argue that while the idea is intriguing, it must be grounded in observable facts and testable predictions to gain broader acceptance. The hypothesis has influenced other areas of research, such as the study of dark matter and dark energy. These mysterious components of the universe might be better understood through the lens of a black hole-based cosmological model. Public interest in the hypothesis has also grown, fueled by popular science books, documentaries, and media coverage. This increased visibility has helped to foster a broader appreciation for the complexities of modern cosmology. Educational institutions and research organizations are investing in the study of black holes and related phenomena. These efforts are helping to train the next generation of scientists who will continue to explore these profound questions. Conferences and workshops dedicated to the hypothesis are becoming more common, providing forums for scientists to share their latest findings and ideas. These events are crucial for advancing the field and fostering collaboration. The hypothesis remains a vibrant topic of discussion within the scientific community. It embodies the spirit of scientific inquiry, pushing the boundaries of what we know and challenging us to think beyond conventional limits. As research continues, the hypothesis that our universe might be inside a black hole will undoubtedly evolve. Whether it is ultimately proven or refuted, it will leave a lasting impact on our understanding of the cosmos and the nature of reality. General relativity, proposed by Albert Einstein in 1915, fundamentally changed our understanding of gravity. It describes gravity not as a force, but as the curvature of space-time caused by mass and energy. According to general relativity, massive objects like stars and planets bend the fabric of space-time around them. This curvature affects the paths of objects and light, creating what we perceive as gravitational attraction. One of the most fascinating predictions of general relativity is the existence of black holes. These are regions where space-time curvature becomes so extreme that nothing, not even light, can escape their gravitational pull. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. If the core's mass is above a certain threshold, it continues to collapse, forming a singularity surrounded by an event horizon. The singularity is a point of infinite density, where the laws of physics as we know them break down. The event horizon is the boundary beyond which nothing can return, effectively making the black hole a one-way gate. General relativity predicts that time behaves differently near a black hole. As an object approaches the event horizon, an outside observer would see its time slow down, a phenomenon known as time dilation. The Schwarzschild solution to Einstein's equations describes a non-rotating black hole. This solution provides the foundation for understanding the simplest type of black hole, with a perfectly spherical event horizon. Rotating black holes, described by the Kerr solution, have more complex properties. Their rotation creates an ergosphere, a region outside the event horizon where spacetime itself is dragged around the black hole. Charged black holes, known as Reissner-Nordstrom black holes, include an electric charge. This adds another layer of complexity to their gravitational field, influencing the behavior of particles and light near them. Black holes can also merge, producing gravitational waves. These ripples in spacetime were first directly detected by the LIGO and Virgo observatories, confirming another key prediction of general relativity. Gravitational lensing is another effect predicted by general relativity. Light passing near a black hole is bent by its intense gravitational field, often creating multiple images or distorted views of background objects. General relativity also predicts the existence of Hawking radiation, a theoretical effect where black holes emit particles due to quantum effects near the event horizon. This radiation causes black holes to lose mass over time. The study of black holes continues to test the limits of general relativity. Observations of black hole behavior and properties provide crucial insights into the nature of gravity and the fabric of spacetime. General relativity's predictions have been confirmed by numerous experiments and observations, solidifying its status as one of the most successful theories in physics. However, black holes remain one of its most mysterious and intriguing predictions. As our observational capabilities improve, general relativity will continue to guide our understanding of black holes and their role in the universe. These enigmatic objects offer a unique window into the deepest workings of space, time, and gravity. Quantum mechanics is the branch of physics that deals with the behavior of particles on the smallest scales. It introduces concepts like wave-particle duality, uncertainty, and quantization of energy levels. These principles challenge our classical understanding of the universe. Black holes, with their extreme gravitational fields, present a unique challenge to quantum mechanics. The combination of general relativity and quantum mechanics leads to complex and sometimes paradoxical situations. One of the most famous paradoxes is the black hole information paradox. According to quantum mechanics, information about a physical system should never be lost. However, if something falls into a black hole, general relativity suggests that its information is lost forever at the singularity. Stephen Hawking proposed that black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. This phenomenon, known as Hawking radiation, implies that black holes can gradually lose mass and eventually evaporate. Hawking radiation arises from virtual particle-antiparticle pairs that form near the event horizon. One particle falls into the black hole while the other escapes, making it appear as if the black hole is radiating particles. The emission of Hawking radiation leads to the gradual shrinking of the black hole. Over incredibly long timescales, this process could result in the complete evaporation of the black hole, leaving behind only radiation. The black hole information paradox remains a significant problem in theoretical physics. If black holes evaporate completely, what happens to the information that fell into them? This question challenges the foundations of quantum mechanics and general relativity. String theory and its extension, M-theory, offer potential resolutions to this paradox. These theories suggest that information might be preserved in subtle ways, perhaps encoded on the event horizon in a manner consistent with the holographic principle. The holographic principle proposes that all the information within a volume of space can be described by the information on its boundary. This idea aligns with the concept that the universe could be a projection from a two-dimensional surface, possibly the event horizon of a higher dimensional black hole. Quantum entanglement, another key concept in quantum mechanics, might also play a role in understanding black holes. Entangled particles remain connected in such a way that the state of one instantly influences the state of the other, regardless of distance. Entanglement could provide insights into how information is shared and preserved in black holes. Some theories suggest that the interior of a black hole is connected to the exterior through entangled particles, helping to resolve the information paradox. The study of quantum gravity seeks to develop a unified theory that combines quantum mechanics and general relativity. Such a theory would provide a complete description of black holes and their quantum properties. Loop quantum gravity is one approach to quantum gravity that attempts to describe the quantum nature of spacetime itself. It suggests that spacetime has a discrete structure, which could influence the behavior of black holes on the smallest scales. Research into the quantum aspects of black holes is ongoing, with many open questions and challenges. Advances in both theoretical and experimental physics are needed to fully understand the interplay between quantum mechanics and black holes. Black holes serve as a testing ground for our theories of physics, pushing the limits of our knowledge and understanding. The interplay between quantum mechanics and black holes continues to inspire new ideas and discoveries in the quest to unravel the mysteries of the universe. Multiverse theory is the idea that our universe might be just one of many universes, collectively known as the multiverse. This concept challenges the traditional view that our universe is the only one that exists. There are several versions of the multiverse theory, each with its own implications and origins. One of the most well-known is the many worlds interpretation of quantum mechanics, which suggests that every possible outcome of a quantum event occurs in its own separate universe. Another version comes from cosmic inflation theory, which posits that different regions of space might undergo inflation at different rates, leading to the creation of separate bubble-like universes. These bubble universes could have different physical laws and constants. String theory also supports the idea of a multiverse. According to string theory, the fundamental components of the universe are one-dimensional strings that vibrate at different frequencies. The theory allows for multiple solutions, each corresponding to a different universe with its own distinct properties. The concept of parallel universes, where alternate versions of events and outcomes exist, is another aspect of the multiverse theory. These parallel universes might be similar to our own or radically different, depending on the variations in their initial conditions. The idea of a multiverse helps address some puzzling questions in cosmology, such as the fine-tuning problem. Our universe appears to be finely tuned for the existence of life, and the multiverse theory suggests that this is just one of many possible universes, some of which may not support life at all. The anthropic principle, which states that we observe certain properties of the universe because they allow for our existence, is often invoked in the context of the multiverse. If many universes exist, it's not surprising that at least one of them has the right conditions for life. Evidence for the multiverse is indirect and largely theoretical. Observations of the cosmic microwave background radiation, the distribution of galaxies, and the behavior of fundamental particles provide some clues, but direct evidence remains elusive. Critics of the multiverse theory argue that it is inherently untestable and therefore falls outside the realm of empirical science. Without the ability to observe or interact with other universes, the theory remains speculative. Despite these challenges, the multiverse theory has gained traction among many physicists and cosmologists. It provides a framework for understanding phenomena that are difficult to explain within the confines of a single universe. Some researchers are exploring ways to test the multiverse theory indirectly. For example, if bubble universes collide, they might leave detectable imprints on the cosmic microwave background radiation. Searching for such imprints could provide evidence for the existence of other universes. The multiverse theory also has philosophical implications, prompting questions about the nature of reality and our place within it. If multiple universes exist, what does that mean for our understanding of existence and the nature of consciousness? In popular culture, the multiverse theory has captured the imagination of writers, filmmakers, and artists. It has inspired numerous stories and scenarios, exploring the idea of alternate realities and the possibilities they present. The study of the multiverse continues to push the boundaries of theoretical physics and cosmology. As our understanding of the universe deepens, the multiverse theory remains a fascinating and provocative concept, challenging us to rethink the nature of reality and the cosmos. While the multiverse theory is still a topic of debate and exploration, it represents one of the boldest and most imaginative ideas in modern science. It opens new avenues for research and offers a broader perspective on the universe and our place within it. Several cosmological models support the idea that our universe might be inside a black hole. These models attempt to bridge the gap between general relativity and quantum mechanics, offering new perspectives on the nature of the cosmos. One of the key models is the holographic principle, which suggests that all the information within a volume of space can be described by information on its boundary. This idea aligns with the notion that our universe could be a projection from a higher dimensional surface. Another important model is the ADS-CFT correspondence, proposed by Juan Maldacena. This theoretical framework relates a type of spacetime called anti-de Sitter space to a conformal field theory. It provides a mathematical basis for understanding how our universe could be connected to a higher dimensional black hole. The ekpyrotic model, a cyclic universe theory, suggests that our universe undergoes endless cycles of expansion and contraction. In this model, the Big Bang is replaced by a Big Bounce, where a previous universe collapsed and rebounded, possibly within a black hole in a higher dimensional space. Loop quantum gravity, an approach to unifying general relativity and quantum mechanics, proposes that space-time has a discrete structure. This theory suggests that black holes might not contain singularities, but instead feature quantum bridges to other regions of space-time, potentially including other universes. The causal set theory, which posits that space-time is composed of discrete elements arranged in a partially ordered set, also supports the idea. In this model, the structure of space-time at the Planck scale could allow for connections between different regions, including black holes and other universes. Inflationary cosmology, which explains the rapid expansion of the early universe, provides another supporting framework. Some versions of this theory suggest that different regions of space could inflate at different rates, creating separate pocket universes within a larger multiverse. Brane cosmology, derived from string theory, envisions our universe as a three-dimensional brane embedded in a higher dimensional space. Interactions between branes, including collisions, could give rise to events like the Big Bang, possibly within black holes in higher dimensions. The concept of quantum foam, which describes the turbulent and fluctuating nature of space-time at the smallest scales, suggests that black holes could serve as portals or tunnels to other regions of space-time, potentially including other universes. Cosmic censorship hypothesis, which posits that singularities are hidden within event horizons, aligns with the idea that our universe could be shielded from other regions of space-time by the event horizon of a black hole in a higher dimension. The black hole firewall hypothesis, which explores the nature of the event horizon and the fate of information falling into a black hole, raises questions about the connection between the interior and exterior regions of black holes, possibly hinting at connections to other universes. The no-boundary proposal, developed by Stephen Hawking and James Hartle, suggests that the universe could have originated from a finite, boundaryless state. This model supports the idea that the universe could have emerged from a black hole-like condition in a higher dimensional space. The multiverse hypothesis, which posits the existence of multiple universes with different physical laws and constants, naturally complements the idea that our universe could be one of many, potentially linked through black holes. Observations of dark energy and the accelerating expansion of the universe suggest that unknown forces are at work. These phenomena could be explained by the influence of a higher dimensional space, consistent with the idea of our universe being inside a black hole. The study of cosmic microwave background radiation provides clues about the early universe that can be compared with predictions from these cosmological models. Subtle features in this radiation might support the idea of a higher dimensional origin for our universe. These cosmological models offer a variety of frameworks for understanding how our universe might be connected to black holes and higher dimensions. While many questions remain, the continued exploration of these ideas promises to deepen our understanding of the fundamental nature of reality. Einstein's field equations form the cornerstone of general relativity, describing how matter and energy in the universe influence the curvature of space-time. These equations underpin our understanding of black holes and cosmological models. The Schwarzschild solution to Einstein's field equations describes a static, spherically symmetric black hole. This solution provides the mathematical foundation for understanding the simplest type of black hole, with no charge or angular momentum. The Kerr metric extends the Schwarzschild solution to include rotating black holes. This metric accounts for the effects of rotation, introducing the concept of the ergosphere, where spacetime itself is dragged around by the black hole's rotation. The Reissner-Nordström solution further generalizes the Schwarzschild metric by incorporating electric charge. This solution describes a charged, non-rotating black hole, adding complexity to the gravitational field and spacetime structure. The Penrose diagram is a graphical representation of spacetime that helps visualize the causal structure of black holes. It shows how light cones and event horizons are affected by the curvature of spacetime near a black hole. Hawking radiation is a theoretical prediction derived from quantum field theory in curved spacetime. It suggests that black holes emit radiation due to quantum effects near the event horizon, leading to the gradual loss of mass and eventual evaporation. The holographic principle proposes that all the information within a volume of space can be encoded on its boundary. This principle, inspired by black hole thermodynamics, suggests that our three-dimensional universe could be a projection from a two-dimensional surface. The Bekenstein-Hawking entropy formula relates the entropy of a black hole to the area of its event horizon. This equation indicates that the information content of a black hole is proportional to the surface area of the event horizon, not its volume. The ADS-CFT correspondence, or Maldacena duality, posits a relationship between a gravitational theory in anti-de Sitter space and a conformal field theory on its boundary. This duality provides insights into the nature of quantum gravity and black holes. The Wheeler-DeWitt equation attempts to combine general relativity and quantum mechanics by describing the quantum state of the entire universe. It plays a crucial role in the study of quantum cosmology and the early universe. Loop quantum gravity introduces the concept of spin networks to describe the quantum geometry of spacetime. These networks provide a discrete structure for spacetime, offering a potential resolution to the singularities predicted by classical general relativity. The Friedmann equations, derived from Einstein's field equations, describe the expansion of the universe. These equations incorporate factors such as the density of matter, dark energy, and the curvature of spacetime to model the dynamics of cosmic expansion. The inflationary theory introduces a scalar field, known as the inflaton, to explain the rapid expansion of the early universe. The potential energy of the inflaton field drives this expansion, leading to the creation of a homogeneous and isotropic universe. Quantum entanglement describes a phenomenon where particles become interconnected, such that the state of one instantly influences the state of another, regardless of distance. Entanglement may provide insights into the information paradox and the nature of spacetime connections. The cosmic microwave background radiation, a relic from the early universe, provides crucial data for testing cosmological models. Tiny fluctuations in this radiation offer evidence for inflation and the large-scale structure of the universe. These key equations and concepts form the foundation of our understanding of black holes, cosmology, and the potential connection between our universe and higher dimensional spaces. They guide ongoing research and help unravel the profound mysteries of the cosmos. The event horizon of a black hole is the boundary beyond which nothing can escape. It marks the point where the gravitational pull becomes so strong that not even light can escape its grasp. As an object approaches the event horizon, the effects of gravity become increasingly extreme. Time appears to slow down for the object relative to a distant observer, a phenomenon known as time dilation. To an outside observer, an object falling towards the event horizon seems to slow down and never actually crosses it. Instead, it appears to freeze and gradually fade away as its light is redshifted to longer wavelengths. For the object itself, however, the experience is quite different. As it crosses the event horizon, it would not notice anything unusual at that precise moment. The event horizon is not a physical barrier, but a point of no return. Once inside the event horizon, the object's fate is sealed. It is drawn inexorably towards the singularity, the point of infinite density at the black hole's core. The gravitational forces become unimaginably strong. These forces cause what is known as spaghettification. The object is stretched and compressed into a long, thin shape due to the intense tidal forces. This effect becomes more pronounced as the object moves closer to the singularity. The event horizon also has profound implications for information. According to the laws of quantum mechanics, information about the physical state of objects should not be lost. However, it appears that information crossing the event horizon might be lost forever, leading to the black hole information paradox. Hawking radiation, which arises from quantum effects near the event horizon, adds another layer of complexity. This radiation suggests that black holes can emit particles and gradually lose mass, challenging our understanding of information and entropy. The surface of the event horizon itself is a dynamic place. It can be influenced by incoming matter and radiation, and it can change in size and shape depending on the black hole's mass and spin. In the case of rotating black holes, the event horizon is accompanied by an ergosphere, a region outside the horizon where spacetime is dragged around by the black hole's rotation. Objects within the ergosphere can still escape, but they must gain energy from the black hole's rotation. The concept of firewalls has been proposed to resolve the black hole information paradox. According to this idea, a highly energetic region, or firewall, exists at the event horizon, destroying anything that crosses it. This concept is still debated among physicists. The behavior of light near the event horizon is also fascinating. Light can orbit the black hole at specific radii known as photon spheres. Within these spheres, the paths of light are bent so severely that they can circle the black hole multiple times. The event horizon's properties are not just theoretical. Observations from the Event Horizon Telescope have provided the first direct images of the event horizon's shadow, offering valuable insights into the nature of black holes. Understanding what happens at the event horizon helps physicists probe the limits of general relativity and quantum mechanics. It challenges them to develop new theories that can reconcile these fundamental aspects of our understanding of the universe. The study of the event horizon continues to be a major focus of research, as it holds the key to some of the deepest mysteries in physics. It pushes the boundaries of our knowledge and invites us to explore the unknown. As an object crosses the event horizon of a black hole, it begins an inevitable journey towards the singularity. The singularity is the core of the black hole, a point where the curvature of space-time becomes infinite and the laws of physics as we know them cease to function. The first effect an object experiences as it moves towards the singularity is the immense increase in gravitational pull. This increase in gravity causes significant tidal forces, stretching the object lengthwise and compressing it sideways in a process known as spaghettification. Closer to the singularity, these tidal forces become even more extreme. The difference in gravitational pull between different parts of the object becomes so great that it is pulled apart atom by atom, molecule by molecule. As the object continues to fall, space and time become increasingly distorted. From the perspective of an outside observer, the object's descent appears to slow down, and it seems to freeze in place near the event horizon. However, from the object's own perspective, time continues normally. Inside the event horizon, all paths lead towards the singularity. The space-time curvature ensures that the object cannot avoid this fate. No matter which direction it tries to move, it will be pulled towards the singularity. In this region, the concepts of past and future become intertwined in ways that are difficult to comprehend. The singularity represents a point where our current understanding of time breaks down. Approaching the singularity, the density of matter and energy becomes infinitely large. This leads to the breakdown of general relativity, as the equations that describe the gravitational field become undefined. Quantum mechanics also faces challenges near the singularity. The principles that govern the behavior of particles on the smallest scales cannot easily be reconciled with the infinite densities predicted by general relativity. Some theories suggest that a complete theory of quantum gravity might resolve these issues. Such a theory would unify general relativity and quantum mechanics, providing a coherent description of the forces at play near the singularity. Loop quantum gravity, for instance, proposes that spacetime has a discrete structure which might prevent the formation of a true singularity. Instead, there could be a minimum length scale that changes the nature of the spacetime fabric at very small scales. String theory offers another possible resolution by suggesting that fundamental particles are not point-like, but rather one-dimensional strings. These strings might behave differently near the singularity, altering the expected outcome. The journey towards the singularity also raises questions about the nature of information. According to quantum mechanics, information should be preserved, but it's unclear how this happens in the context of black holes and singularities. Some scientists propose that information is encoded on the event horizon and can be recovered from the Hawking radiation emitted by the black hole. This idea aligns with the holographic principle, but remains a topic of intense debate. Ultimately, the singularity represents one of the greatest mysteries in modern physics. It challenges our understanding of the universe and pushes us to develop new theories that can describe the fundamental nature of reality. The study of singularities is not just theoretical. By observing black holes and their effects on surrounding matter, scientists can gather data that might help answer these profound questions. The journey towards the singularity continues to captivate and inspire the scientific community. Theoretical scenarios inside a black hole delve into some of the most complex and speculative aspects of physics. One scenario suggests that the interior of a black hole could connect to another region of spacetime, potentially creating a wormhole. Wormholes are hypothetical passages through spacetime that could connect distant points in the universe. If a black hole's singularity is linked to another universe or a different part of our own, it might act as a bridge. Another scenario involves the concept of a white hole, which is the theoretical opposite of a black hole. While black holes draw matter in, white holes are thought to expel matter. Some theories propose that the matter falling into a black hole might emerge from a white hole in another part of spacetime. In the context of string theory, black holes might not contain singularities but rather extremely dense states of strings. These strings could form a fuzzball structure, eliminating the problematic singularity and replacing it with a complex network of strings. Loop quantum gravity offers a different perspective, suggesting that the singularity might be replaced by a quantum bounce. In this scenario, the collapsing matter inside a black hole could reach a minimum size and then rebound, possibly creating a new universe. Holographic principles also play a role in theorizing about black hole interiors. If our universe is a hologram projected from the event horizon, the black hole's interior might be a three-dimensional representation of information encoded on a two-dimensional surface. Some scientists speculate that the intense gravitational forces inside a black hole could lead to the formation of exotic states of matter. These states, governed by the principles of quantum mechanics, might exhibit properties we have yet to discover or understand. The firewall hypothesis suggests that an observer falling into a black hole would encounter a highly energetic firewall at the event horizon. This firewall would incinerate anything crossing it, presenting a controversial solution to the information paradox. There's also the notion that black holes could be regions where spacetime undergoes extreme warping, creating a bubble universe. Inside this bubble, the laws of physics might differ significantly from those outside the black hole. In speculative scenarios, the inside of a black hole might contain different dimensions. If extra dimensions exist, as suggested by string theory, black holes could provide a gateway to these hidden realms, altering our perception of space and time. The study of Hawking radiation suggests that black holes emit particles and gradually lose mass. This process could reveal insights about the quantum state of the black hole's interior, potentially uncovering how information is preserved. Information theory also proposes that the interior of a black hole could be described entirely by the information encoded on its event horizon. This idea aligns with the holographic principle and offers a way to reconcile the loss of information with quantum mechanics. There are theories that propose black holes as cosmic seeds. These seeds could trigger the formation of new galaxies or even new universes. If true, the interior dynamics of black holes could play a crucial role in the large-scale structure of the cosmos. Some models suggest that black holes might be cosmic computers, processing information in ways that could affect the entire universe. This concept ties into the idea of the universe as a vast information network, with black holes as key nodes. Finally, the true nature of spacetime inside a black hole remains one of the greatest mysteries in physics. Whether it leads to another universe, contains exotic states of matter, or represents a profound quantum state, the interior of a black hole continues to challenge our understanding and inspire new theories. The concept of spacetime fabric is central to our understanding of black holes. According to general relativity, massive objects like stars and planets warp the fabric of spacetime, creating what we perceive as gravity. A black hole represents an extreme warping of this fabric. When a massive star collapses under its own gravity, it can create a region where space-time curvature becomes so intense that it forms an event horizon. Within the event horizon, space-time is bent so sharply that all paths lead to the singularity. The singularity is a point of infinite density, where our current laws of physics cannot describe the conditions. The event horizon itself is a dynamic boundary. It can expand or contract depending on the black hole's mass and the matter and energy it absorbs. This boundary is crucial in defining the black hole's influence on spacetime. Spacetime near a black hole is highly distorted. This distortion affects the paths of particles and light, leading to phenomena such as gravitational lensing, where light bends around the black hole, creating multiple images or arcs of background objects. The ergosphere of a rotating black hole adds another layer of complexity. In this region, space and time are dragged around the black hole, allowing energy to be extracted from the black hole's rotation through processes like the Penrose process. Gravitational waves, ripples in the fabric of spacetime, are generated by the acceleration of massive objects, such as when black holes merge. These waves carry information about the black hole's properties and the nature of spacetime. Black holes also impact the fabric of spacetime on a quantum level. The interplay between general relativity and quantum mechanics near a black hole's event horizon leads to complex behaviors, such as Hawking radiation, which arises from quantum effects. The study of black holes provides insights into the nature of spacetime itself. By observing how black holes warp spacetime, scientists can test theories of gravity and explore the fundamental structure of the universe. In the context of string theory, the fabric of spacetime might have additional dimensions beyond the familiar three spatial dimensions and one time dimension. Black holes could interact with these extra dimensions, influencing their structure and behavior. Loop quantum gravity proposes that spacetime has a discrete structure at the smallest scales. This theory suggests that near a black hole's singularity, the continuous fabric of spacetime might break down into a network of quantum loops. The holographic principle implies that the information within a volume of spacetime can be represented on a lower dimensional boundary. This idea challenges our conventional understanding of spacetime and offers new ways to think about black holes. Black holes also raise questions about the nature of time. Near a black hole, time dilation becomes extreme, with time slowing down significantly for an observer close to the event horizon compared to someone far away. The concept of space-time fabric also extends to cosmology. The large-scale structure of the universe, including the distribution of galaxies and dark matter, is influenced by the warping of spacetime by massive objects like black holes and galaxy clusters. Understanding spacetime fabric and black holes helps us probe the deepest questions in physics. These enigmatic objects challenge our understanding and push the boundaries of what we know about the universe's fundamental nature. The ongoing study of black holes and their impact on spacetime continues to reveal new insights and inspire the quest for a unified theory of physics. Comparing black holes to the observable universe reveals intriguing similarities and stark contrasts. Both black holes and the universe exhibit behaviors that challenge our understanding of physics. The observable universe is vast, encompassing all the matter, energy, and space we can detect. In contrast, a black hole is a region of space where gravity is so intense that nothing can escape from it, not even light. The universe is expanding, with galaxies moving away from each other, driven by dark energy. Black holes, on the other hand, are regions where matter collapses to a point, creating extreme densities and gravitational fields. The cosmic microwave background radiation provides a snapshot of the universe when it was just 380,000 years old. This ancient light offers clues about the universe's early conditions and its large-scale structure. Black holes also emit radiation, known as Hawking radiation, due to quantum effects near their event horizons. The distribution of galaxies and dark matter in the universe forms a cosmic web with clusters, filaments, and voids. Black holes can be found at the centers of galaxies, often influencing the dynamics and evolution of their host galaxies. The observable universe is governed by the laws of general relativity and quantum mechanics. Black holes are key objects where these laws intersect, leading to complex and sometimes paradoxical behaviors that push the limits of our understanding. Dark matter makes up about 27% of the universe's total mass and energy, influencing the formation and stability of galaxies. Inside black holes, the nature of matter is pushed to extreme conditions, potentially revealing new states of matter and energy. Dark energy, responsible for the accelerated expansion of the universe, remains one of the greatest mysteries in cosmology. The dynamics inside black holes might offer insights into the fundamental nature of this mysterious force. The universe's large-scale structure and evolution are studied through observations of distant galaxies, cosmic microwave background radiation, and gravitational waves. Black holes are studied through their interactions with surrounding matter, their gravitational waves, and the effects of their intense gravitational fields. Both black holes and the universe as a whole are connected through the concept of entropy. The Bekenstein-Hawking entropy formula relates the entropy of a black hole to the area of its event horizon. The entropy of the universe is related to its volume and the distribution of matter and energy. The formation of black holes from collapsing stars and the potential birth of new universes from black holes suggest a cyclical nature of cosmic events. The universe itself might undergo cycles of expansion and contraction, as proposed by some cosmological models. Comparing the observable universe to the interior of a black hole raises profound questions about the nature of spacetime. If our universe is inside a black hole, the event horizon might represent the boundary of our observable universe, with unknown regions beyond. The study of black holes provides a microcosm for understanding the universe's fundamental principles. By probing the extreme conditions inside black holes, scientists can gain insights into the behavior of space, time, and matter under the most intense gravitational forces. The relationship between black holes and the universe is also explored through the concept of cosmic censorship, which posits that singularities are hidden within event horizons. This idea has implications for the structure and fate of the universe. Both black holes and the universe challenge us to rethink our understanding of reality. They push the boundaries of theoretical physics, inspiring new theories and models that seek to explain the deepest mysteries of the cosmos. As research continues, comparing black holes with the observable universe will remain a fruitful area of inquiry. It offers the potential to unlock new discoveries and deepen our understanding of the universe's origin, structure, and ultimate fate. Telescopic observations have revolutionized our understanding of black holes. By observing the light and radiation emitted by matter around black holes, astronomers can infer the presence and properties of these enigmatic objects. The Event Horizon Telescope made history in 2019 by capturing the first direct image of a black hole's shadow. This supermassive black hole is located in the galaxy M87, and its shadow provided visual evidence of the event horizon. X-ray telescopes like Chandra and XMM Newton detect the high-energy X-rays emitted by hot gas spiraling into black holes. These observations reveal the intense gravitational forces at play and the dynamic processes occurring near the event horizon. Radio telescopes, such as those used in the Event Horizon Telescope Array, can observe the emissions from jets and accretion disks around black holes. These observations help scientists study the magnetic fields and relativistic particles in the vicinity of black holes. Infrared telescopes, like the Spitzer Space Telescope, can peer through dust clouds that often obscure black holes in visible light. By observing in infrared, astronomers can study the environments of black holes in greater detail. Optical telescopes, such as the Hubble Space Telescope, have provided stunning images of galaxies with active supermassive black holes at their centers. These images show the effects of black holes on their host galaxies, including energetic outflows and jets. The Keck Observatory in Hawaii has played a crucial role in studying the motions of stars near the center of the Milky Way. These observations provided strong evidence for the existence of a supermassive black hole, known as Sagittarius A. Gravitational wave observatories like LIGO and Virgo have detected the ripples in spacetime caused by black hole mergers. These observations confirm the predictions of general relativity and provide new insights into the properties of black holes. Gamma-ray telescopes, such as Fermi, detect the high-energy gamma rays emitted by black hole jets and gamma-ray bursts. These observations help scientists understand the extreme environments around black holes and the processes that produce such energetic emissions. The Very Large Telescope in Chile has been instrumental in observing the dynamics of stars and gas around supermassive black holes. These observations help map the gravitational potential and mass distribution near black holes. The James Webb Space Telescope, set to provide unprecedented resolution and sensitivity, will allow astronomers to study the formation and growth of black holes in the early universe. It will observe the faint infrared signals from distant galaxies and their central black holes. Observations of black hole binaries, where a black hole orbits a companion star, provide valuable information about black hole masses and spins. Telescopes across the electromagnetic spectrum contribute to these studies by observing the emissions from the accretion disks and jets. The Gaia spacecraft, which maps the positions and motions of stars in the Milky Way, can identify black hole candidates by detecting the gravitational influence of unseen companions on visible stars. This data helps estimate the number and distribution of black holes in our galaxy. Future telescopes, such as the Square Kilometre Array, will vastly increase our ability to detect and study black holes. With greater sensitivity and resolution, these telescopes will uncover more about the population and properties of black holes across the universe. Telescopic observations continue to push the boundaries of our knowledge, revealing the fascinating and complex nature of black holes. By combining data from multiple telescopes and wavelengths, astronomers piece together a more complete picture of these mysterious objects. As technology advances, our understanding of black holes and their role in the cosmos will only deepen, opening new frontiers in astrophysics and cosmology. Gravitational waves are ripples in the fabric of spacetime, predicted by Einstein's theory of general relativity. They are produced by some of the most violent and energetic processes in the universe. When massive objects like black holes or neutron stars accelerate, they can create gravitational waves. These waves travel at the speed of light, carrying information about their origins and the nature of gravity itself. The detection of gravitational waves was achieved by the Laser Interferometer Gravitational Wave Observatory, or LIGO, in 2015. This groundbreaking discovery confirmed a major prediction of general relativity. LIGO's interferometers work by measuring tiny changes in the distance between mirrors caused by passing gravitational waves. These changes are incredibly small, less than the width of a proton, but detectable with advanced technology. The first gravitational wave detected by LIGO came from the merger of two black holes about 1.3 billion light-years away. This event, named GW150914, provided direct evidence of black hole mergers and opened a new window into the cosmos. Following LIGO's success, the Virgo interferometer in Italy joined the search for gravitational waves. Together, LIGO and Virgo have detected multiple events, including black hole mergers and neutron star collisions. Gravitational waves from neutron star mergers offer unique insights because these events also produce electromagnetic radiation, such as gamma-ray bursts. By observing both gravitational and electromagnetic signals, scientists can learn more about the physics of these catastrophic events. The study of gravitational waves has led to the field of multi-messenger astronomy, where different types of signals from the same event are analyzed together. This approach provides a more comprehensive understanding of cosmic phenomena. Gravitational waves can also test fundamental aspects of physics. For instance, they allow scientists to measure the speed of gravity, which should be the same as the speed of light according to general relativity. The detection of gravitational waves from black hole mergers helps determine the properties of black holes, such as their masses and spins. These observations provide clues about the formation and evolution of black holes. Gravitational waves can carry information about the early universe, potentially revealing conditions just moments after the Big Bang. This makes them a powerful tool for studying cosmology and the origins of the universe. Advanced LIGO and Virgo upgrades are increasing the sensitivity of these detectors, allowing them to observe more events and gather more data. Future detectors, like the space-based LISA, will further expand our ability to detect gravitational waves. LISA, the Laser Interferometer Space Antenna, is expected to launch in the 2030s. It will be capable of detecting lower-frequency gravitational waves, such as those from supermassive black hole mergers, which are beyond the reach of ground-based detectors. The discovery of gravitational waves has sparked interest in new theories of gravity and spacetime. Researchers are exploring concepts like modified gravity and extra dimensions to explain observations that might deviate from general relativity. Gravitational wave astronomy is still in its early stages, but it has already revolutionized our understanding of the universe. As technology advances and more detectors come online, the study of gravitational waves will continue to reveal new and exciting aspects of the cosmos. Hawking radiation is a theoretical prediction by physicist Stephen Hawking, suggesting that black holes can emit radiation due to quantum effects near their event horizons. This phenomenon challenges the classical view that nothing can escape from a black hole. The concept of Hawking radiation arises from the interaction between quantum mechanics and general relativity. Near the event horizon, particle-antiparticle pairs can spontaneously form from the vacuum of space. In the presence of a black hole, one of these particles can fall into the black hole while the other escapes. To an outside observer, it appears as if the black hole is emitting particles, leading to what we call Hawking radiation. This process causes the black hole to lose mass over time. As it emits radiation, it gradually shrinks and can eventually evaporate completely if it does not accrete new matter. Hawking radiation is incredibly weak for large black holes, making it challenging to detect with current technology. The radiation becomes more significant for smaller black holes, where the emission rate increases as the black hole's mass decreases. The discovery of Hawking radiation was groundbreaking because it suggested that black holes are not entirely black, but have a temperature and can radiate energy. This realization connects the thermodynamics of black holes with quantum field theory. The temperature of a black hole due to Hawking radiation is inversely proportional to its mass. Large black holes have very low temperatures, while smaller black holes can have much higher temperatures. The existence of Hawking radiation leads to the black hole information paradox. If a black hole can evaporate completely, what happens to the information about the matter that fell into it? This question challenges the principle that information must be conserved in quantum mechanics. Various solutions to the information paradox have been proposed, including the idea that information is somehow encoded in the Hawking radiation, or that it is preserved on the event horizon through the holographic principle. Hawking's prediction also implies that primordial black holes, which might have formed in the early universe, could be sources of detectable Hawking radiation today. These tiny black holes would emit significant amounts of radiation as they evaporate. The study of Hawking radiation has inspired new research into the quantum properties of black holes and the nature of spacetime. It has opened up new avenues for exploring the intersection of quantum mechanics and general relativity. Although direct detection of Hawking radiation remains elusive, researchers continue to develop experiments and observations to test the theory. This includes looking for signatures of evaporating primordial black holes. Hawking radiation has also influenced theoretical physics, leading to the development of concepts like black hole thermodynamics and the holographic principle. These ideas have far-reaching implications for our understanding of the universe. The implications of Hawking radiation extend to the fate of the universe. If black holes can evaporate over time, it could influence the long-term evolution of galaxies and cosmic structures. Stephen Hawking's work on black hole radiation has left a lasting legacy in the field of theoretical physics. It continues to inspire new research and deepen our understanding of the mysterious and fascinating nature of black holes. As we develop more advanced technologies and theoretical frameworks, the study of Hawking radiation will remain a key area of exploration in our quest to understand the universe. Black hole mergers are among the most powerful events in the universe. When two black holes orbit each other and eventually collide, they create gravitational waves that ripple through spacetime. These mergers provide a unique opportunity to study black holes and test the predictions of general relativity. The gravitational waves produced carry information about the masses, spins, and other properties of the merging black holes. The first direct detection of gravitational waves from a black hole merger was made by LIGO in 2015. This historic event, known as GW 150914, confirmed the existence of black hole mergers and opened a new era in astronomy. The gravitational waves from GW 15094 were produced by the collision of two black holes, each about 30 times the mass of the Sun. The merger created a single black hole with a mass of about 62 solar masses, with the remaining mass converted into energy carried away by the gravitational waves. Black hole mergers occur in regions of space where black holes can come close enough to be influenced by each other's gravity. This often happens in dense environments like globular clusters or galactic centers. As the black holes spiral closer together, they lose energy through the emission of gravitational waves. This process, called inspiral, continues until the black holes reach a point where they merge into a single, more massive black hole. The final stages of a black hole merger are incredibly violent and energetic. The merged black hole often exhibits a ring-down phase, where it emits gravitational waves as it settles into a stable state. Observations of black hole mergers help scientists understand the population of black holes in the universe. By analyzing the properties of the merging black holes, researchers can infer how they formed and evolved over time. The detection of black hole mergers also provides insights into the behavior of matter and energy in extreme gravitational fields. These observations test the limits of general relativity and help refine our theoretical models. Future gravitational wave detectors, such as the space-based LISA, will be able to observe mergers of supermassive black holes. These events occur when galaxies merge and their central black holes collide, producing even more powerful gravitational waves. Black hole mergers are not only important for studying gravity, but also for understanding the formation and growth of galaxies. The mergers of supermassive black holes influence the dynamics and evolution of their host galaxies. The discovery of black hole mergers has led to the development of numerical relativity, where supercomputers simulate the dynamics of black hole collisions. These simulations help predict the gravitational wave signals that detectors like LIGO and Virgo observe. The study of black hole mergers also has implications for the search for dark matter. Some theories propose that dark matter could form black hole-like objects, and their mergers might produce detectable gravitational waves. Black hole mergers are a key component of multi-messenger astronomy. By combining gravitational wave data with electromagnetic observations, scientists can gain a more comprehensive understanding of these events. As more black hole mergers are detected, our understanding of these fascinating objects and their role in the universe will continue to grow. The study of black hole mergers is a vibrant and rapidly advancing field, promising new discoveries and insights into the nature of gravity and the cosmos. The ongoing observation of black hole mergers will provide crucial data for testing our theories of physics and exploring the mysteries of the universe. These events are a testament to the power and complexity of black holes and their profound impact on the fabric of spacetime. Potential signs within our universe that could indicate it is inside a black hole come from various observations and theoretical predictions. These signs include the behavior of cosmic expansion, the properties of dark energy, and the structure of spacetime. One potential sign is the accelerated expansion of the universe. Dark energy is driving this acceleration, and its mysterious nature might be linked to the effects of being inside a black hole. The outward push of dark energy could mirror the expansive properties expected within a black hole. The cosmic microwave background radiation provides a snapshot of the early universe. Subtle anomalies in this radiation might hint at the influence of higher dimensional space, consistent with the idea of our universe residing in a black hole. Gravitational waves, ripples in spacetime caused by massive cosmic events, could also offer clues. The patterns and frequencies of these waves might reveal underlying structures that suggest a connection to a higher dimensional black hole. The distribution of galaxies and large-scale structures in the universe forms a cosmic web, with clusters, filaments, and voids. This intricate arrangement might reflect the influence of a black hole's gravitational field on a grand scale. Black holes themselves offer potential signs. Observing the behavior of supermassive black holes at the centers of galaxies, including their growth and interactions, could provide indirect evidence of our universe's unique position within a larger structure. The concept of holography suggests that all the information in our three-dimensional universe might be encoded on a two-dimensional surface. If true, this principle could support the idea that our universe is a projection from an event horizon of a higher dimensional black hole. Examining the properties of black holes, such as their entropy and temperature, might also reveal patterns that align with the characteristics of our universe. These properties could reflect a deeper connection between black holes and cosmic evolution. Theoretical models involving string theory propose that extra dimensions influence the behavior of particles and forces in our universe. Signs of these extra dimensions, potentially detected through high-energy particle experiments, might indicate a black hole's presence in higher dimensional space. The behavior of dark matter, an unseen component that makes up most of the universe's mass, might be influenced by the conditions of being inside a black hole. Studying dark matter's distribution and interaction could provide insights into this possibility. Anomalies in the laws of physics at extreme scales, such as near black holes or at the universe's edge, might suggest influences from a higher dimensional black hole. These anomalies could be detected through precise astronomical and physical measurements. The study of black hole thermodynamics and information theory might uncover principles that apply to the universe as a whole. These principles could reveal signs that our universe is subject to the same rules as a black hole. Investigating the fate of black holes and their eventual evaporation through Hawking radiation might provide parallels to the long-term evolution of the universe. Understanding these processes could hint at a deeper connection between black holes and cosmic destiny. Examining cosmic inflation, the rapid expansion that occurred moments after the Big Bang, might reveal conditions similar to those expected within a black hole. Inflationary models that include extra dimensions could support the hypothesis. Research into the fundamental nature of time, particularly its behavior near black holes, and in the early universe might offer clues. If time behaves differently within a black hole, similar patterns could be reflected in the universe's overall structure. Finally, the quest for a unified theory of quantum gravity seeks to combine general relativity and quantum mechanics. Success in this endeavor might naturally lead to a deeper understanding of black holes and potentially confirm our universe's place within one. Exploring these potential signs will continue to push the boundaries of our knowledge, offering new perspectives on the cosmos and our place within it. Redefining our understanding of the universe involves challenging long-held assumptions and integrating new ideas that arise from cutting-edge research. The hypothesis that our universe might be inside a black hole is one such idea, pushing the boundaries of cosmology and physics. If the universe is inside a black hole, it suggests that our cosmic horizon is analogous to an event horizon. This redefinition implies that what we perceive as the edge of the observable universe could be a boundary with profound implications for space and time. This perspective encourages us to rethink the Big Bang. Instead of being an isolated event, the Big Bang could be seen as a transition phase within a black hole, connecting our universe to a larger, higher dimensional space. Such a hypothesis aligns with the holographic principle, proposing that all information within our universe is encoded on a two-dimensional surface. This idea fundamentally changes our conception of dimensions and the nature of reality. Understanding the universe as a black hole also impacts our views on entropy and thermodynamics. It suggests that the universe's entropy might be related to the surface area of its cosmic horizon, mirroring black hole thermodynamics. The concept of dark energy, which drives the accelerated expansion of the universe, could be reinterpreted. It might be linked to the properties of the higher dimensional space in which our universe resides, offering new insights into its mysterious nature. Redefining the universe in this way challenges the notion of isolated singularities. If our universe is inside a black hole, singularities might be points of connection to other regions of space-time or other universes, suggesting a complex, interconnected multiverse. This hypothesis also influences our understanding of time. Time dilation near an event horizon could provide insights into the flow of time within our universe, affecting our theories on the universe's beginning and ultimate fate. By redefining the universe as a black hole, we open up new avenues for exploring the fundamental laws of physics. It encourages the development of theories that unify general relativity and quantum mechanics, advancing our quest for a theory of everything. The study of cosmic inflation, dark matter, and gravitational waves can be integrated into this new framework. Each of these phenomena might be better understood through the lens of a universe residing within a black hole, offering more cohesive explanations. This redefinition encourages interdisciplinary collaboration. Astrophysicists, cosmologists, and theoretical physicists must work together to explore the implications, combining observational data with theoretical models to test and refine the hypothesis. The hypothesis also has philosophical implications. It invites us to reconsider our place in the cosmos and the nature of existence, prompting deeper questions about reality and our understanding of the universe. Educational approaches to cosmology and physics would need to adapt, incorporating these new ideas into curricula and research programs. This shift would inspire future generations of scientists to explore the frontiers of knowledge. Public interest in the universe and black holes would likely increase, driven by the profound and intriguing nature of these ideas. Communicating these concepts effectively can inspire curiosity and wonder about the cosmos. Ultimately, redefining our understanding of the universe to include the possibility of being inside a black hole is a transformative idea. It pushes the boundaries of science, challenges our perceptions, and opens new pathways for discovery and exploration in our quest to understand the true nature of the cosmos. The hypothesis that our universe might be inside a black hole has profound implications for the Big Bang theory. It suggests a new perspective on the origin and evolution of the universe. Traditionally, the Big Bang theory posits that the universe began from an extremely hot and dense singularity approximately 13.8 billion years ago. If our universe is within a black hole, this initial singularity could be reinterpreted. Instead of a singular point, the Big Bang could represent the formation of a black hole in a higher dimensional space. This black hole might connect our universe to a larger cosmos, fundamentally altering our understanding of the Big Bang. This perspective provides a potential explanation for the uniformity of the cosmic microwave background radiation. The conditions inside a black hole could drive a more homogeneous and isotropic expansion, explaining this observed uniformity. It also impacts our understanding of cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. Inflation could be seen as a natural consequence of the dynamics within a black hole, smoothing out the universe's structure. The idea aligns with the holographic principle, suggesting that the information in our universe is encoded on a two-dimensional boundary. This principle could offer a new framework for understanding the distribution of matter and energy in the early universe. Considering the universe as a black hole also addresses the horizon problem, where regions of space far apart appear to have the same temperature. The connectivity within a black hole might allow for faster information exchange, solving this puzzle. This hypothesis challenges the concept of a unique singularity. The Big Bang might be just one of many such events, each corresponding to a black hole formation in different regions of a higher dimensional cosmos. It also influences the idea of the multiverse. If our universe is inside a black hole, countless other universes could exist within other black holes, each with its own Big Bang-like event and subsequent evolution. The notion reshapes our understanding of time. The time before the Big Bang could be linked to processes in the higher dimensional space, suggesting a continuous, rather than a discrete, beginning of time. This perspective impacts the entropy of the universe. The initial low entropy state of the universe might be explained by the thermodynamic properties of black holes, providing a new context for the second law of thermodynamics. It also offers new insights into dark matter and dark energy. These components, which dominate the universe's mass and energy, could be influenced by the properties of the black hole in which our universe resides. The hypothesis prompts a re-evaluation of the cosmic microwave background's slight anisotropies. These temperature variations could be linked to the intricate structure and dynamics within a black hole. It suggests a deeper connection between quantum mechanics and cosmology. Understanding the quantum properties of black holes could shed light on the quantum state of the early universe. Finally, this hypothesis inspires new theoretical models and simulations. Researchers can explore how black hole dynamics affect cosmic evolution, leading to a more comprehensive understanding of the Big Bang and the universe's growth. The impact on the Big Bang theory is profound, challenging established ideas and offering a richer, more complex picture of the universe's origin and evolution. This perspective opens new avenues for exploration and deepens our quest to understand the cosmos. The idea that our universe might be inside a black hole has significant implications for multiverse theories. It suggests a more interconnected and dynamic relationship between different universes. If each black hole in our universe contains another universe, this supports the concept of an infinite multiverse. Each universe could spawn countless other universes through black hole formations, creating an ever-expanding web of interconnected realities. This perspective aligns with the many worlds interpretation of quantum mechanics. In this view, every possible outcome of a quantum event occurs in its own separate universe, further enriching the multiverse with diverse histories and futures. The hypothesis provides a new context for cosmic inflation. Different regions of space might inflate at different rates, creating separate bubble universes. Each of these bubbles could be a black hole in a higher dimensional space, connecting them to a larger multiverse. It also supports the idea of parallel universes, where alternate versions of events and outcomes exist. If our universe is inside a black hole, it might be one of many parallel universes within a vast higher dimensional framework. The concept of a black hole multiverse suggests that the laws of physics could vary from one universe to another. Each black hole could lead to a universe with different physical constants and laws, explaining the fine-tuning observed in our own universe. This idea influences the anthropic principle, which states that we observe certain properties of the universe because they allow for our existence. In a black hole multiverse, many universes might not support life, making our universe's conditions seem less unique. The hypothesis encourages the exploration of how information is transferred between universes. If information can cross the event horizon of a black hole, it might be preserved or altered, influencing the state of the resulting universe. It also impacts our understanding of time. The flow of time might differ between universes, especially near the event horizons of black holes. This could lead to diverse temporal structures and histories within the multiverse. The idea supports the concept of a cyclic universe. Black holes might not be the end of their host universes, but the beginning of new ones. This cyclical process could create an endless series of births and rebirths within the multiverse. It suggests that singularities might not be endpoints but gateways. The singularity at the center of a black hole could connect to the Big Bang of a new universe, linking different regions of the multiverse through these transitional points. The hypothesis has implications for string theory, which proposes that extra dimensions influence the fundamental nature of reality. Black holes in higher dimensional spaces might connect these dimensions, creating diverse and complex universes. It also encourages new theoretical models and simulations. By studying the dynamics of black holes and their connections to other universes, researchers can develop more comprehensive multiverse theories that account for these interactions. This perspective enriches our understanding of the large-scale structure of the cosmos. It suggests that the observable universe is just one part of a much larger and more intricate multiverse, filled with interconnected and interdependent regions. Finally, the idea inspires new questions and explorations. How do black hole dynamics influence the evolution of their host universes? What happens to the information that crosses the event horizon? These questions drive ongoing research and deepen our understanding of the multiverse. The influence on multiverse theories is profound, expanding our view of reality and opening new pathways for discovery. The hypothesis that our universe might be inside a black hole inspires the development of new cosmological models. These models aim to integrate the dynamics of black holes with the structure and evolution of the cosmos. One such model involves the concept of a black hole universe, where each black hole in our universe leads to a new, distinct universe. This fractal-like structure suggests a self-similar pattern at every scale, with universes nested within black holes. Another model explores the idea of a cyclic universe. In this scenario, the universe undergoes infinite cycles of expansion and contraction. Black holes play a crucial role in this model, acting as gateways between different phases of the universe's life cycle. String theory offers models where extra dimensions are fundamental. These models propose that black holes can influence or be influenced by these hidden dimensions, leading to a more complex understanding of spacetime and cosmic evolution. The ekpyrotic model is another alternative, suggesting that our universe was created from the collision of two higher dimensional branes. This collision could be analogous to the formation of a black hole, providing a new perspective on the Big Bang. Quantum gravity models, such as loop quantum gravity, propose that spacetime is quantized at the smallest scales. These models suggest that black holes do not contain singularities, but instead feature quantum bridges to other regions of spacetime. The multiverse model extends the idea of multiple universes, each with its own laws of physics. Black holes could serve as connections between these universes, allowing for the transfer of matter, energy, and information. Inflationary models continue to evolve, incorporating the dynamics of black holes. These models suggest that different regions of space might inflate at different rates, creating bubble universes connected through black hole structures. The holographic principle inspires models where the universe is viewed as a hologram. In these models, all the information within a volume of space can be encoded on a lower dimensional boundary, potentially an event horizon. Some cosmological models explore the role of dark energy and dark matter in a black hole universe. These models aim to explain how these mysterious components influence the structure and expansion of the cosmos when viewed through the lens of black hole dynamics. Theories of modified gravity also emerge, proposing changes to Einstein's general relativity to account for observations at cosmic scales. These models explore how black hole dynamics might fit into a modified framework of gravity. Cosmological models now incorporate the study of gravitational waves. These waves, produced by black hole mergers, provide new data to test theories and refine our understanding of the universe's structure and evolution. Observational models focus on detecting signs of black hole influence in the cosmic microwave background radiation and the large-scale distribution of galaxies. These models use data from telescopes and satellites to compare predictions with actual observations. Numerical simulations play a critical role in developing new cosmological models. Supercomputers simulate the dynamics of black holes, galaxy formation, and cosmic evolution, providing insights that guide theoretical developments. These new cosmological models push the boundaries of our understanding, integrating black hole dynamics with the broader framework of the universe. They challenge traditional views and offer fresh perspectives on the fundamental nature of reality. As research continues, these models will evolve, incorporating new data and refining their predictions. They hold the potential to revolutionize our understanding of the cosmos, offering a more interconnected and comprehensive view of the universe and its origins. The potential for future research into the idea that our universe might be inside a black hole is vast and exciting. As our observational and theoretical tools improve, we can explore this hypothesis in greater depth. One area of research involves improving our understanding of black hole dynamics. By studying the behavior of black holes in more detail, we can gather clues about the potential connections between black holes and the broader universe. Gravitational wave astronomy will play a crucial role. Advanced detectors like LIGO, Virgo, and future observatories such as LISA will provide more data on black hole mergers and other cataclysmic events, offering insights into the fabric of spacetime. Researchers are developing more sophisticated simulations of black holes and their interactions. These simulations will help us understand the possible structures within black holes and how they might relate to the structure of our universe. Exploring the properties of dark matter and dark energy is another critical area. Understanding these mysterious components of our universe could reveal how they are influenced by or connected to black holes in higher dimensions. The study of the cosmic microwave background radiation continues to be essential. Future missions will provide even more precise measurements, potentially uncovering subtle patterns that support the hypothesis of a black hole universe. Quantum gravity remains a frontier in theoretical physics. Researchers are working on unifying general relativity and quantum mechanics, which could lead to a better understanding of black holes and the origins of our universe. The role of extra dimensions, as proposed by string theory, offers another avenue for exploration. Investigating how these dimensions interact with our observable universe and black holes could provide significant breakthroughs. The development of new telescopes and observational technologies will enhance our ability to study black holes and their effects on surrounding matter and spacetime. These advancements will bring us closer to testing the hypothesis directly. Interdisciplinary research is crucial. Collaboration between cosmologists, theoretical physicists, and astronomers will foster new ideas and approaches, integrating diverse perspectives to tackle the complexities of a black hole universe. Exploring the information paradox and black hole thermodynamics will continue to be a focus. Resolving these paradoxes might provide the key to understanding the deeper connections between black holes and the cosmos. Public engagement and education will also be important. As these ideas gain traction, effectively communicating the science to a broader audience will inspire future generations of researchers and foster a deeper appreciation for the mysteries of the universe. International cooperation in space missions and research projects will enhance our capabilities. Combining resources and expertise from around the world will accelerate discoveries and the development of new technologies. Ethical considerations will also play a role as we delve deeper into these profound questions. Understanding the implications of our research on the nature of reality and existence will be essential in guiding our exploration responsibly. Finally, the potential for unexpected discoveries is immense. As we explore these ideas, we might uncover new principles of physics, unexpected phenomena, and deeper truths about the universe that we have yet to imagine. The future of research into the possibility that our universe is inside a black hole is bright and filled with promise. It challenges us to think beyond conventional limits, inspiring new questions and opening pathways to a deeper understanding of the cosmos. The hypothesis that our universe might be inside a black hole faces significant scientific criticisms. One primary criticism is the lack of direct observational evidence. While the idea is intriguing, it remains speculative without empirical support. Critics argue that the hypothesis relies heavily on theoretical constructs that are challenging to test. Concepts like higher dimensions, the holographic principle, and black hole thermodynamics are difficult to verify experimentally. Another criticism is that the hypothesis complicates rather than simplifies our understanding of the universe. Adding layers of higher dimensional spaces and multiple black hole universes might not provide the most straightforward explanations for observed phenomena. Skeptics point out that existing cosmological models, such as the Standard Model of Cosmology, already explain many observations without invoking black hole universes. These models account for the cosmic microwave background radiation, large-scale structure, and cosmic inflation effectively. The hypothesis also raises questions about the nature of singularities. If each black hole leads to a new universe, it implies an infinite regress of black holes within black holes, which some scientists find problematic and overly complex. Another significant criticism is the issue of information loss. While the idea of black hole universes might address some aspects of the information paradox, it does not provide a clear solution to how information is preserved or transmitted across event horizons. The hypothesis's reliance on string theory and other speculative frameworks is another point of contention. While these theories offer fascinating possibilities, they remain unproven and controversial within the scientific community. Practical difficulties in testing the hypothesis also pose a challenge. Observing the interior of a black hole directly, or detecting signs of higher dimensional influences, is beyond our current technological capabilities, making the hypothesis hard to falsify. Some critics argue that the hypothesis might be an example of overextending theoretical physics. It pushes the boundaries of our current understanding, but may lack the grounding necessary to be considered a robust scientific theory. The hypothesis's implications for the nature of time and causality also draw criticism. If our universe is inside a black hole, the conventional understanding of time's flow and causality could be fundamentally altered, raising questions about the consistency of physical laws. Another criticism is the potential for alternative explanations. Many phenomena that the black hole universe hypothesis aims to explain might be accounted for by other, more conventional theories that do not require such radical assumptions. The hypothesis's impact on the Big Bang theory is also debated. While it offers an alternative view of the universe's origin, it may not necessarily provide a better explanation than the Standard Model, which has extensive observational support. Critics also highlight the philosophical implications of the hypothesis. It raises profound questions about the nature of reality and our place in the cosmos, which some argue are speculative and beyond the scope of empirical science. There are concerns about the mathematical complexity of the hypothesis. The models and equations involved are highly complex and may not yield clear, testable predictions, limiting their usefulness in advancing our understanding. Despite these criticisms, the hypothesis continues to inspire discussion and research. It challenges scientists to think creatively and explore new ideas, even as they work to address its many challenges and limitations. The debate itself drives the progress of science, pushing the boundaries of what we know and encouraging deeper exploration of the universe's mysteries. Proving the hypothesis that our universe might be inside a black hole presents significant logistical challenges. One of the main difficulties is the inability to directly observe the interior of a black hole, as no information can escape past the event horizon. Another challenge is the scale of the phenomena involved. The immense distances and energies associated with black holes and cosmic events make it difficult to gather data or conduct experiments that can provide conclusive evidence. Current technology limits our ability to detect higher dimensional spaces or the effects of such dimensions on our universe. Instruments capable of probing these dimensions are still in the realm of theoretical development. Gravitational wave detectors, while advanced, may not have the sensitivity required to detect subtle signatures that could indicate our universe's black hole nature. Future advancements in this technology will be necessary to explore this possibility further. Simulating the complex interactions within black holes and their potential connections to other universes requires enormous computational power. Even with supercomputers, creating accurate models of such interactions is a formidable task. The hypothesis also demands new theoretical frameworks that unify general relativity and quantum mechanics. Developing a consistent theory of quantum gravity is one of the most challenging problems in physics and is essential for validating the hypothesis. Empirical tests of the hypothesis are difficult because they often rely on indirect evidence. Observing anomalies in cosmic microwave background radiation or large-scale cosmic structures might provide hints, but not definitive proof. The hypothesis requires collaboration across multiple disciplines, including cosmology, quantum mechanics, and string theory. Coordinating such interdisciplinary research efforts poses logistical challenges in terms of communication and integration of different methodologies. Funding for research into such speculative areas can be difficult to secure. Many scientific funding bodies prioritize projects with clear, immediate applications, or those that build on well-established theories, making it hard to support such cutting-edge research. Ethical considerations also play a role in the logistical challenges. Ensuring that the pursuit of such speculative hypotheses does not divert resources from other important scientific research is a delicate balance that needs careful management. Developing new experimental techniques is essential but time-consuming and expensive. Innovations like advanced particle accelerators or space-based observatories require significant investment and international cooperation. Interpreting data in the context of this hypothesis is complex. Subtle signals might be easily misinterpreted, and distinguishing between potential indicators of a black hole universe and other cosmic phenomena requires rigorous analysis and peer review. Public perception and understanding of such advanced scientific concepts can influence funding and support for research. Educating the public and policymakers about the importance and potential of this research is crucial but challenging. Maintaining the scientific rigor required to explore this hypothesis involves constantly testing and refining models, theories, and experimental methods. This ongoing process is resource-intensive and demands a sustained commitment from the scientific community. Despite these logistical challenges, the pursuit of understanding whether our universe might be inside a black hole drives innovation and advances in multiple fields of science. The process of addressing these challenges pushes the boundaries of our knowledge and capabilities, leading to new discoveries and technologies that benefit all areas of research. Physicists have raised several counterarguments against the hypothesis that our universe might be inside a black hole. One primary argument is the lack of direct observational evidence to support such a claim, making it speculative and not empirically grounded. Another counterargument focuses on the existing cosmological models, which adequately explain the observed phenomena without needing to invoke the concept of our universe being inside a black hole. These models, based on general relativity and the standard model of cosmology, are well supported by data. Critics argue that the hypothesis complicates our understanding of the universe rather than simplifying it. Introducing higher dimensional spaces and multiple nested universes may not offer the most straightforward explanations for the observations we have. The concept of a black hole universe implies an infinite regress of black holes within black holes, which some physicists find problematic. This idea seems overly complex and lacks a clear mechanism for how such a structure could form or sustain itself. Another significant counterargument is the issue of information loss. While the black hole universe hypothesis might address some aspects of the information paradox, It does not provide a clear solution to how information is preserved or transmitted across event horizons. The hypothesis heavily relies on speculative frameworks like string theory and the holographic principle, which are not universally accepted or experimentally verified. This reliance on unproven theories weakens the overall credibility of the hypothesis. Practical difficulties in testing the hypothesis also pose a challenge. Observing the interior of a black hole directly or detecting signs of higher dimensional influences is beyond our current technological capabilities, making the hypothesis hard to falsify. Some physicists argue that the hypothesis might be an example of overextending theoretical physics. It pushes the boundaries of our current understanding, but may lack the grounding necessary to be considered a robust scientific theory. The hypothesis's implications for the nature of time and causality are also debated. If our universe is inside a black hole, the conventional understanding of time's flow and causality could be fundamentally altered, raising questions about the consistency of physical laws. Critics highlight that many phenomena the black hole universe hypothesis aims to explain might be accounted for by other, more conventional theories that do not require such radical assumptions. This suggests that the hypothesis might not be necessary to explain these observations. The potential philosophical implications of the hypothesis also raise concerns. It suggests a reality far more complex and interconnected than currently understood, which some argue ventures into the realm of metaphysics rather than empirical science. Mathematical complexity is another point of criticism. The models and equations involved in the hypothesis are highly complex and may not yield clear, testable predictions, limiting their usefulness in advancing our understanding. The impact on the Big Bang theory is also debated. While the hypothesis offers an alternative view of the universe's origin, it may not necessarily provide a better explanation than the standard model, which has extensive observational support. The hypothesis might divert attention and resources from other important areas of research. Critics argue that focusing on more established theories and models, which have a clearer path to empirical testing, might be a more productive approach. Despite these counterarguments, the hypothesis continues to inspire discussion and research. It challenges scientists to think creatively and explore new ideas, even as they work to address its many challenges and limitations. The debate itself drives the progress of science, pushing the boundaries of what we know and encouraging deeper exploration of the universe's mysteries. The technological limitations in proving whether our universe is inside a black hole are substantial. Current telescopes and detectors are not equipped to observe the interior of a black hole directly, as no information can escape from beyond the event horizon. Gravitational wave detectors like LIGO and Virgo have advanced our understanding, but they still lack the sensitivity needed to detect subtle signatures that could indicate a higher dimensional black hole structure. Future advancements in this technology will be necessary. High-energy particle accelerators, such as the Large Hadron Collider, can probe the fundamental particles and forces, but they cannot reach the energy scales required to test the effects of extra dimensions directly. New, more powerful accelerators would be needed. Simulating the complex interactions within black holes and their potential connections to other universes demands enormous computational power. Even with supercomputers, creating accurate and comprehensive models of such interactions is a formidable challenge. Current space telescopes like Hubble and future projects like the James Webb Space Telescope can provide detailed observations of the universe, but are limited in their ability to detect the higher dimensional influences proposed by the hypothesis. The development of instruments capable of probing these extra dimensions is still in the theoretical stage. It requires innovative approaches and significant investment in research and development to move from concept to practical application. Quantum gravity experiments, essential for unifying general relativity and quantum mechanics, are currently beyond our reach. Developing a consistent theory of quantum gravity remains one of the most challenging problems in modern physics. Directly observing or measuring the holographic principle's effects is another technological hurdle. While the principle is intriguing, detecting its manifestations in the universe requires advancements in both theoretical understanding and observational techniques. The potential for discovering primordial black holes and their Hawking radiation remains limited by our current observational capabilities. Detecting the weak radiation emitted by these small black holes is a significant technical challenge. Collaboration across multiple disciplines, including cosmology, quantum mechanics, and string theory, is crucial but logistically challenging. Coordinating such interdisciplinary research efforts involves overcoming communication and methodological barriers. Funding for research into such speculative areas can be difficult to secure. Many scientific funding bodies prioritize projects with clear, immediate applications or those that build on well-established theories, making it hard to support cutting-edge, high-risk research. Developing new experimental techniques is essential but time-consuming and expensive. Innovations like advanced particle accelerators or space-based observatories require significant investment and international cooperation to realize their potential. Interpreting data in the context of this hypothesis is complex. Subtle signals might be easily misinterpreted, and distinguishing between potential indicators of a black hole universe and other cosmic phenomena requires rigorous analysis and peer review. Public perception and understanding of such advanced scientific concepts can influence funding and support for research. Educating the public and policymakers about the importance and potential of this research is crucial but challenging. Despite these technological limitations, the pursuit of understanding whether our universe might be inside a black hole drives innovation and advances in multiple fields of science. Addressing these challenges pushes the boundaries of our knowledge and capabilities, leading to new discoveries and technologies that benefit all areas of research. As technology advances, the possibility of testing and proving or disproving this hypothesis becomes more feasible, opening new pathways for understanding the universe. The hypothesis that our universe might be inside a black hole has profound philosophical implications. It challenges our understanding of reality and our place in the cosmos. If our universe is inside a black hole, it suggests that our reality is part of a much larger and more complex structure. This idea expands our perspective beyond the confines of our observable universe. This hypothesis raises questions about the nature of existence. Are there multiple levels of reality, each with its own set of physical laws and constants? How do these different realities interact with one another? The concept of a black hole universe suggests that the boundaries of our reality are defined by the event horizon. This challenges our understanding of space and time, implying that they are more fluid and interconnected than we previously thought. It also brings into question the nature of singularities. If singularities are gateways to other universes, then the point of infinite density is not an end, but a transition to another reality. This idea redefines the concept of beginning and end in the cosmos. The hypothesis impacts our understanding of time. If time flows differently within a black hole, it suggests that our perception of past, present, and future might be an illusion shaped by the structure of our universe. The idea of a multiverse, with countless universes nested within black holes, suggests that our universe is just one of many. This perspective can be both humbling and liberating, as it places our existence within a vast, interconnected web of realities. It challenges the anthropocentric view of the universe. If there are countless other universes, each with its own conditions and inhabitants, then our universe is not uniquely special, but part of a grander cosmic tapestry. The hypothesis also raises questions about the nature of consciousness. If our reality is shaped by the structure of a black hole, what does this mean for the nature of mind? Are there different forms of consciousness in other universes? It brings into focus the limits of human knowledge. The idea that our universe might be inside a black hole suggests that there are aspects of reality that are fundamentally beyond our grasp, challenging us to continually expand our understanding. The hypothesis impacts ethical considerations. If our universe is part of a larger structure, then our actions might have consequences beyond our own reality. This perspective encourages a more holistic and interconnected view of ethics. It also influences our approach to science and exploration. Understanding that we are part of a black hole universe motivates us to push the boundaries of knowledge and seek answers to the most profound questions about existence. The idea of a black hole universe redefines our understanding of cosmology. It encourages the development of new theories and models that integrate the dynamics of black holes with the broader structure of the cosmos. It raises questions about the nature of reality itself. Is the universe a holographic projection, a complex network of interactions, or something entirely different? These questions challenge us to rethink our assumptions about the nature of existence. Finally, the hypothesis inspires a sense of wonder and curiosity. It reminds us that the universe is far more mysterious and complex than we can imagine, encouraging us to explore, question, and seek deeper understanding. The philosophical implications of this hypothesis are profound, challenging us to reconsider our place in the cosmos and the nature of reality itself. It pushes the boundaries of human thought and invites us to explore the deepest mysteries of existence. The holographic principle is a groundbreaking idea that suggests all the information in our universe can be described by information on a lower dimensional boundary. This principle emerged from studies of black hole thermodynamics and string theory. According to the holographic principle, the three-dimensional world we experience might be a projection from a two-dimensional surface, much like a hologram. This concept challenges our conventional understanding of dimensions and reality. The principle was first proposed by Gerard de Hooft and further developed by Leonard Susskind. They were inspired by the entropy of black holes, which is proportional to the area of their event horizons, not their volume. This idea aligns with the properties of black holes. When an object falls into a black hole, its information is encoded on the event horizon. This encoding preserves the information, suggesting that the surface holds all the necessary data about the object's properties. The ADS-CFT correspondence formulated by Juan Maldacena provides a concrete example of the holographic principle. It shows a relationship between a gravitational theory in anti-de Sitter space and a conformal field theory on the boundary, supporting the idea of a holographic universe. The holographic principle has profound implications for our understanding of the universe. It suggests that space and time might emerge from more fundamental entities, changing how we perceive the fabric of reality. In cosmology, the principle offers a new perspective on the early universe and the Big Bang. It implies that the initial conditions of the universe could be encoded on a two-dimensional surface, influencing its subsequent evolution. This principle also impacts our understanding of black holes. If all the information about a black hole's interior is stored on its event horizon, it might resolve the black hole information paradox, which questions whether information is lost when objects fall into a black hole. The holographic principle has applications in various fields of physics, including quantum gravity, string theory, and condensed matter physics. It provides a unifying framework for understanding different aspects of physical phenomena. In the context of quantum mechanics, the principle suggests that the behavior of particles and forces can be described by information on a lower dimensional boundary. This perspective could help bridge the gap between general relativity and quantum mechanics. Experimental tests of the holographic principle are challenging but ongoing. Researchers are exploring ways to detect holographic properties in high-energy particle collisions and other phenomena, seeking empirical support for this theoretical concept. The principle also has philosophical implications. It challenges our notions of space, time, and reality, suggesting that what we perceive as a three-dimensional world might be a projection from a deeper, more fundamental layer of existence. Understanding the holographic principle requires rethinking our assumptions about the nature of the universe. It encourages the development of new theories and models that incorporate this idea, pushing the boundaries of theoretical physics. The holographic principle continues to inspire research and exploration. It offers a revolutionary perspective on the nature of reality, suggesting that our universe is far more intricate and interconnected than we can imagine. As research progresses, the holographic principle may provide deeper insights into the fundamental workings of the cosmos. It represents a bold and innovative approach to understanding the universe, opening new pathways for discovery and expanding our horizons in physics and cosmology. String theory is a theoretical framework that aims to unify all fundamental forces and particles in the universe. It proposes that the basic building blocks of the universe are not point-like particles, but one-dimensional strings that vibrate at different frequencies. These strings can stretch, contract, and combine in various ways, creating the diverse particles and forces we observe. The different vibrational modes of the strings correspond to different particles, such as quarks, electrons, and photons. String theory requires additional dimensions beyond the familiar 3 spatial dimensions and 1 time dimension. In most versions, there are 10 or 11 dimensions, with the extra dimensions being compactified or hidden at very small scales. The theory emerged in the late 20th century as a potential solution to several fundamental problems in physics. It offers a way to reconcile general relativity, which describes gravity, with quantum mechanics, which describes the behavior of particles on the smallest scales. One of the most compelling aspects of string theory is its potential to provide a unified description of all fundamental forces. This includes gravity, electromagnetism, and the strong and weak nuclear forces, which are traditionally described by different theories. String theory also introduces the concept of supersymmetry, which suggests that every particle has a superpartner with different properties. Supersymmetry could help explain the relative strengths of the forces and solve other puzzles in particle physics. The theory has led to the development of various models, including Type I, Type IIA, Type IIB, heterotic, and M-theory. Each version has different characteristics and explores different aspects of the fundamental nature of strings. One of the key successes of string theory is the AD-CFT correspondence, proposed by Juan Maldacena. This duality relates a gravitational theory in a higher dimensional space to a conformal field theory on its boundary, providing insights into both quantum gravity and gauge theories. Despite its potential, string theory remains unproven and controversial. Critics argue that it has not yet made definitive, testable predictions and relies on mathematical constructs that are difficult to verify experimentally. Testing string theory poses significant challenges due to the high energy scales required to probe the extra dimensions in string dynamics. Current technology and experiments are not yet capable of reaching these energy levels. String theory also faces competition from other approaches to quantum gravity, such as loop quantum gravity. These alternative theories offer different perspectives on the unification of forces and the structure of spacetime. Supporters of string theory believe that its mathematical beauty and consistency provide strong evidence for its validity. They argue that the theory's ability to incorporate all known forces and particles into a single framework is a significant achievement. Research in string theory continues to advance, with physicists exploring its implications for cosmology, black holes, and the early universe. The theory has also influenced other areas of theoretical physics, leading to new ideas and techniques. String theory's potential to explain the fundamental nature of reality inspires ongoing investigation and debate. It represents one of the most ambitious and comprehensive efforts to understand the universe at its deepest level. As research progresses, string theory may provide new insights into the fundamental workings of the cosmos, offering a path toward a unified theory of everything. It challenges us to think beyond conventional limits and explore the profound mysteries of the universe. Loop quantum gravity is a theoretical framework that seeks to reconcile general relativity with quantum mechanics. It proposes that spacetime itself has a discrete granular structure at the smallest scales, rather than being a continuous fabric. In loop quantum gravity, spacetime is composed of tiny indivisible loops, called spin networks. These loops are interconnected in a complex web, giving rise to the fabric of spacetime and the geometry of the universe. This theory differs from string theory, which posits one-dimensional strings as the fundamental building blocks. Loop quantum gravity focuses on the quantization of spacetime itself, rather than introducing new fundamental entities. One of the key features of loop quantum gravity is that it predicts a minimum length scale, known as the Planck length. This scale is incredibly small, on the order of 10⁻⁵ meters, and represents the smallest possible unit of space. Loop quantum gravity also introduces the concept of spin foam, which describes the evolution of spin networks over time. Spin foam provides a way to model the dynamic, evolving nature of the quantum geometry of spacetime. The theory offers a potential solution to the problem of singularities in general relativity. In loop quantum gravity, the intense gravitational forces near a singularity are expected to create a quantum bounce, preventing the formation of an infinite density point. This quantum bounce has significant implications for our understanding of black holes and the Big Bang. It suggests that black holes might not contain singularities, but instead feature a region where spacetime is compressed to its minimum scale and then rebounds. Similarly, the Big Bang could be seen as a transition from a previous contracting phase, rather than a singular point of infinite density. This perspective aligns with cyclic models of the universe, where expansion and contraction phases alternate. Loop quantum gravity also has implications for the nature of time. In this framework, time may emerge from the evolution of spin networks, rather than being a fundamental, continuous entity. This idea challenges our conventional understanding of temporal flow. One of the strengths of loop quantum gravity is its background independence. Unlike some other theories, it does not assume a fixed spacetime background. Instead, the geometry of spacetime itself is dynamic and subject to quantum fluctuations. The theory has led to the development of various models and equations that describe the quantum properties of spacetime. These models provide a framework for understanding how gravity operates at the smallest scales. Despite its promise, loop quantum gravity faces significant challenges. One of the main criticisms is the difficulty in making testable predictions. The extremely small scales involved are currently beyond the reach of experimental verification. Researchers are exploring ways to find indirect evidence for loop quantum gravity. This includes studying the cosmic microwave background radiation, gravitational waves, and the behavior of black holes to identify signatures that might support the theory. Loop quantum gravity has also influenced other areas of theoretical physics, including the study of quantum cosmology and black hole thermodynamics. It provides new tools and concepts for exploring the fundamental nature of the universe. As research in loop quantum gravity continues, it holds the potential to deepen our understanding of spacetime and the forces that govern the cosmos. It represents a bold and innovative approach to one of the most profound challenges in modern physics. The pursuit of loop quantum gravity reflects the ongoing quest to unify the laws of physics and unlock the mysteries of the universe. By exploring the quantum structure of spacetime, scientists hope to gain new insights into the nature of reality and the origins of the cosmos. Parallel universe theories suggest that our universe is just one of many, each existing in its own separate realm. These theories propose that multiple universes or multiverses coexist but do not interact directly with each other. One version of parallel universe theories comes from quantum mechanics, specifically the many worlds interpretation. This interpretation suggests that every possible outcome of a quantum event happens in its own distinct universe. According to the many worlds interpretation, every decision or event creates a branching of universes, resulting in an infinite number of parallel realities. Each of these universes follows its own unique timeline and set of circumstances. Another parallel universe theory is based on cosmic inflation. This theory proposes that during the rapid expansion of the early universe, different regions of space expanded at different rates, creating separate bubble universes. These bubble universes could have different physical constants and laws of physics. If true, our universe might be just one bubble in a vast, frothy sea of universes, each with its own characteristics and properties. String theory also supports the idea of parallel universes through the concept of brains. In this framework, our universe could be a three-dimensional brain floating in a higher dimensional space, with other brains representing parallel universes. And these brains could interact in ways that are not immediately obvious. Collisions between brains might even trigger events similar to the Big Bang, giving rise to new universes in the process. The idea of parallel universes raises profound questions about the nature of reality and our place within it. If multiple universes exist, what does that mean for our understanding of existence, identity, and consciousness? Parallel universe theories also challenge the concept of uniqueness. If there are infinite versions of ourselves in different universes, each making different choices and experiencing different outcomes, it redefines our sense of individuality. Testing the existence of parallel universes is a significant challenge. Direct observation is currently impossible, but scientists are exploring indirect methods, such as looking for anomalies in the cosmic microwave background radiation or gravitational waves that might suggest the presence of other universes. Some theories propose that parallel universes might leave subtle imprints on our universe. These imprints could be detectable through precise measurements of cosmic phenomena, offering potential clues about the existence of other realms. The study of parallel universes intersects with many areas of physics, including cosmology, quantum mechanics, and string theory. Researchers are developing models and simulations to explore the implications and potential evidence for these theories. Parallel universe theories also inspire philosophical and metaphysical discussions. They challenge us to rethink our notions of reality, existence, and the nature of the cosmos, pushing the boundaries of both science and philosophy. As research continues, the exploration of parallel universes remains one of the most intriguing and speculative areas of modern science. It opens up possibilities that stretch the imagination and challenge our understanding of the fundamental nature of reality. Whether parallel universes exist or not, the pursuit of these theories drives innovation and exploration in physics, encouraging us to seek deeper understanding and expand our horizons in the quest to uncover the mysteries of the universe. Dark matter and dark energy are two of the most mysterious components of our universe, making up about 27% and 68% of the universe's total mass and energy, respectively. Their elusive nature has profound implications for our understanding of the cosmos. Dark matter does not emit, absorb, or reflect light, making it invisible to current telescopic observations. However, its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. The connection between dark matter and the hypothesis that our universe might be inside a black hole lies in the gravitational effects we observe. These effects could potentially be explained by the influence of higher dimensional structures within a black hole. Dark energy is even more enigmatic. It is thought to be responsible for the accelerated expansion of the universe. Understanding its nature is crucial for explaining the ultimate fate of the universe and its overall structure. If our universe is inside a black hole, dark energy might be related to the properties of the higher dimensional space in which our universe resides. The expansive force of dark energy could be a reflection of the dynamic processes occurring in this higher dimensional space. The study of dark matter and dark energy involves indirect observations. For dark matter, scientists observe the rotation curves of galaxies and the gravitational lensing of distant objects. These phenomena suggest the presence of unseen mass. Dark energy is studied through observations of distant supernovae, the cosmic microwave background radiation, and the large-scale structure of the universe. These observations indicate that the universe's expansion is accelerating, driven by this mysterious energy. Some theories propose that dark matter could consist of exotic particles that interact weakly with normal matter. These particles might be remnants from the early universe, providing clues about the conditions shortly after the Big Bang. The interaction between dark matter and black holes is another area of interest. Dark matter could accumulate around black holes, influencing their growth and the dynamics of their surrounding environments. Dark energy's role in the universe's expansion suggests that it has a repulsive gravitational effect, counteracting the attractive force of gravity. This behavior is still not fully understood and remains one of the biggest challenges in cosmology. If dark energy is connected to the structure of a higher dimensional black hole, it might offer a new perspective on the cosmological constant problem. This problem involves the large discrepancy between theoretical predictions and observed values of dark energy density. Research into dark matter and dark energy involves sophisticated experiments and observations. Projects like the Large Hadron Collider, the Dark Energy Survey, and the upcoming James Webb Space Telescope aim to uncover more about these elusive components. The connection between dark matter, dark energy, and the hypothesis of a black hole universe offers a unified framework for understanding the cosmos. It suggests that these components are not isolated phenomena, but part of a larger, interconnected structure. Future discoveries in particle physics, cosmology, and astrophysics will likely shed more light on these mysteries. By exploring the connections between dark matter, dark energy, and the nature of our universe, scientists hope to unlock deeper insights into the fundamental workings of the cosmos. As we advance our observational and theoretical tools, the quest to understand dark matter and dark energy will continue to be at the forefront of scientific exploration. These efforts will help determine whether our universe's true nature involves being part of a vast, higher dimensional structure akin to a black hole. In this video, we embarked on a fascinating journey exploring the hypothesis that our universe might be inside a black hole. We delved into the origins of this idea, tracing its roots to concepts in general relativity and quantum mechanics, and examined how it challenges our conventional understanding of the cosmos. From the formation and types of black holes to the event horizon and singularity, we uncovered the intricate details of these mysterious objects. We also explored the implications of this hypothesis on the Big Bang theory and multiverse theories, considering how it could reshape our understanding of the universe's origin and structure. The connection between black holes, dark matter, and dark energy open new avenues for understanding the fundamental components of our universe and their interactions. The role of telescopic observations and advancements in technology highlighted the importance of continued exploration. Upcoming missions like the James Webb Space Telescope and the Vera C. Rubin Observatory promise to bring unprecedented clarity and data, propelling our understanding forward. We discussed how these technological advancements, along with quantum computing, could lead to significant breakthroughs in black hole research. Collaboration within the scientific community plays a crucial role in advancing our knowledge. By pooling resources, sharing expertise, and working together on international projects, scientists can tackle the complex challenges presented by black hole studies and related fields. This collaborative spirit is essential for making progress in our quest to understand the universe. We also considered the philosophical implications of the hypothesis, pondering the nature of reality and our place in the cosmos. The holographic principle and string theory provided a theoretical framework for understanding the potential connections between our universe and high-dimensional spaces. Potential breakthroughs in black hole research, driven by advancements in technology and theoretical physics, hold the promise of transforming our understanding of these enigmatic objects and their role in the universe. From detecting Hawking radiation to discovering new types of black holes, the future of black hole studies is bright and full of potential. Thank you for joining us on this journey through the mysteries of black holes and the universe. If you enjoyed this video, please like and subscribe to our channel for more fascinating content. Don't forget to check out our other videos, where we explore various topics in astrophysics, cosmology, and beyond. Your support helps us continue to bring you insightful and engaging content.